There are 2 of these are just myself. So for those of you who are here, could you let me know if you're able to open Colab? You should have, if you just go to colab.research.google.com. So I'll just copy paste that website here in case you want to open it. Where is the chat?
Right on the right side.
Oh,
Yeah.
right. Yeah. So I rarely use Google Meet for teaching. It's mostly MS Teams. Yeah. So
MS Teams is a little bit stiff on its. I don't know. So maybe that is the way administration has set it up. It's a little bit
probably.
stuff about file permissions.
I see. Okay.
So
But I find it to be very convenient because all the students are in one place and it's very easy to interact with them and
that is true.
you
That is
can
true.
share.
That is,
Yeah.
but you don't have any controls over your file. So if you want the students just to view it, not download it, that option you don't
Uh-huh.
have.
Yeah. Yeah. Anyway, all my lecture notes, all my material is open source. So I don't care. Yeah. It doesn't matter if they download it or not. Yeah. Good. So actually, before I start, I should tell you that there might be some interruptions. Okay. So both my cats are sleeping here next to me, but if they get up, they might definitely run over my laptop and
Sure, sure,
there might be some interruptions. So
sure,
if
sure,
that happens, don't worry, I'll just be logging back in couple of
sure,
minutes.
sure, sure, sure. So how many cats do you have?
2.
Oh, okay. Males?
What's that?
Males?
Oh, the younger one is Hobbs. He's just about 4 months old. He's right here.
Okay,
And the older one is Per Elise. She's
okay,
slightly more far away, but yeah.
okay, okay.
Yeah.
Cats can
Yeah.
be fun. We have some feral ones.
Yeah.
They just roam about. Sometimes they come over and eat some food,
Okay, okay.
but they are
Yeah.
nice. At some point in time, we had 7 around us.
Oh, yeah, yeah, that's nice. Yeah, my parents used to have a lot of cats
Okay,
and dogs. Yeah,
okay.
yeah, very nice. Yeah, yeah, I think they add a very nice, beautiful dimension to our lives. So,
Yes, yes.
and also a lot of naughtiness. And,
Yeah, we had to do lots of cleaning around.
yeah, yeah, a lot actually. Yeah, good. Okay, so it's almost time. I just want to know. So can someone from the participant list let me know if you're able to open Colab and you're able to see, you should be seeing something like this. Okay, so once you open your browser and type colab.research.google.com, it should prompt you to open a new notebook, among others. And if you press new notebook, you should be able to see a screen like this. So can someone confirm if they are able to do that? I at least want to know if there's one person who can do it.
So I know Miss Ulia is very responsive. If she could open it, no.
Sir, sorry, pardon, sir.
So Professor
Hello.
Professor Mutan wants to know if you could open the web page that he wants, the Colab web page.
Yes, I already opened, sir.
Okay.
It is
Okay.
opening.
Okay, good, good. And by the way, all of you participants also can call me Amudan, okay? No need to call me professor or sir or something. Yeah, I'm a very informal guy, so it's just calling me Amudan is good. Yeah. Okay, so you should be able to see a document like this. And if you're able to see this, then I think you're mostly set. Okay, so it's going to be a browser-based, a cloud-based, programming interface, which is nice because it saves you a lot of the setup and installation time. I will also send you the link for the material. All the material that I'm going to talk today is open source and it's available freely online. So I'll just post the link here. So in case people join late. So that's my GitHub account. So I've created a separate page for this workshop. So if you go there, you can see both the slides for this workshop and the Python code that I'll be running you through as part of the hands-on sessions. Okay, so you can, if you click this, it should take you hopefully to this web page. Okay, so this is the GitHub web page. So forget about this readme.md. That's just a very simple text file. Basic physics-based learning. That's a IPython notebook that contains all the code that we will be looking at today. And this PDF file that contains the slides that I'll be showing today. Okay, so feel free to download it. Feel free to have a copy with you, whatever works. Okay, good. Can someone let me know before we start if you're able to see this website and open anything there?
So the link you shared, that is opening,
Yeah.
and we can see your screen as well.
My screen. Okay. You mean, do you see something like this? Hello?
In collapse, sir,
No.
that link you shared.
The first link I shared is Colab. The second link I shared here, that you see here, right?
Yes,
GitHub.com.
yes, sir.
Yeah, so if you go
Yes,
there,
sir.
are you able to see this?
1 second, sir. Let me check. Yes, sir.
Great. Okay. So this should get you all the information that you want. Perfect. Okay. I think we're all set.
Okay, sir. Thank you, sir.
So Akshay, let me know when we have to start and we can start. Okay, perfect. So we can start. So just start the slides. So welcome everyone to the final session, final technical session of this workshop. I'm Amudan Ramabhadran. I'm a faculty at assistant professor at IIT Bombay, the Aerospace Engineering Department. And it's very nice to meet some of you here. I was told there will be 60, but then I suppose there are about 8. But 8 is as good a number as any. So nice to see you all. I'll be talking today about physics-based learning. Okay, this is slightly different from what you have been introduced to as part of the optimization workshop, and also probably not something that is typically covered in a traditional optimization workshop kind of a setting, because it's kind of relatively new. Though many of the ideas that I'm talking about have been around for quite some time. Putting them together in the context of what is called as differentiable programming is kind of very popular nowadays. So I thought I'd give you a simple example, a simple introduction to this particular field. Okay, good. Now, here is a rough outline of what I'll be talking about. Okay, so I'll very briefly introduce differentiable physics, and then I'll give an overview of optimization. Luckily for me, the advantage of being the last speaker is that I can build on what people have said before. So in particular, some of the there have been fantastic reviews as part of this workshop on the basics of optimization. So I won't spend a lot of time. I'll very quickly go through that. And then I'll talk a little bit about automatic differentiation, because that is at the heart of most of the optimizations that we would be doing today. And after that, I'll give you a very brief introduction to deep neural networks, because some of the simulations, especially the inverse simulations that we'll be doing, or the forward ones too, will involve the use of neural networks. Okay. And to show an application of all these things, I'll look into ordinary differential equations. Okay, that's reasonably interdisciplinary. I suppose you would find ordinary differential equations in multiple disciplines, irrespective of what your background is. But I thought, to keep it fun, the example I would be doing today is entirely in terms of cricket. Okay, I like cricket a lot, even though I'm not good at any of batting, bowling, or fielding, nothing. But I just love to watch. Okay, so if you see this introductory picture, right? So this is actually wind tunnel visualization of flow past a cricket ball. Okay, and you can see very beautifully that there is flow separation on one side, and whereas the flow is relatively laminar on the other side. And this is in fact what causes the ball to swing. There's a lot of interesting fluid dynamics. We won't be doing that, but I thought it's a nice picture to show. what you would be doing is a simplified version of trajectory simulation of a cricket ball, if we have time and if all goes well. And so that would be our agenda. Okay, so I'll show some simple examples with Pytorch, which is a library for doing for studying neural networks in Python. It's very powerful. And again, if we have time, we can have a small competition at the end. I'm going to ask you to all train your own neural networks and to learn how to bowl. And let's find out who the best bowler is, right? Okay. Uh, Here is the key thing, okay? Before we start, I'm going to assume that you all have a working knowledge of Python. This might be a little unrealistic, I guess. I'm not sure. So I'm just going to very quickly ask you, how many of you here have used Python before or have a working knowledge? I'm just curious to know. Maybe I can open the chat. It's here. Can someone tell me, either on chat or you can unmute yourself? Feel free to do that. If you have worked with Python before. No? Okay. Is there anyone who has worked with Python? Okay, so that's going to make it slightly difficult because I think the work I'll be presenting today builds on top of Python, okay? Which is why I had given a link to some basic Python tutorials in the very first day of the workshop. You should have received it from Professor Akshay. In any case, it's okay. So what, if you don't know Python, then you will not be able to follow many of the precise details of the talk. But I hope you get the larger picture, and I'm pretty sure that you can also pick it up along the way. Python is a very easy language to learn. So even if this serves as a motivation for you to pick up Python later on and then build on top of that, that's good. Okay, good. So let me go back to the slides. Again, I have a slightly different point of view than the other speakers, then, which is that, and I'm not going to ask and stop in the middle and ask if you have any questions or if you have any doubts, because from what I understand, this is a faculty development workshop, and I presume all of you are already self-motivated and you have your own reasons to be here. So I'm going to assume that if you have a question, you will find a way to ask that question. Okay, I'm not going to stop and pause every time and then ask if you have questions. So if you have questions, please stop and ask me. As I said in the beginning, I'm very informal, so always happy to have a chat. Okay, good. Now, let's get started. The subject today is physics-based learning, and I think that that's important to understand what that is. Okay? And I want to highlight that in the context of data-based learning, which is kind of very popular. Okay? And machine learning is all the rage these days. Everyone wants to be inside that. So I suppose most of you, even if you don't work in it, already know what data-based modeling is, right? And again, the theme for today's talk is going to be cricket, because we just won the Test series. Of course, it's a great time to talk about cricket. So here's an example of data about various wind tunnel studies done on the aerodynamics of cricket balls. Okay, this is from this very nice paper by Mehta. So I encourage you to check out this paper if you want to learn more about the physics of cricket balls. And specifically, the question that he addresses there is, how does the ball swing? Okay, so here's a simple schematic which shows you that there's laminar flow on one side, and the rough side you see that there's turbulent flow. And because of the turbulent flow, these flow separates at a later point than on the laminar side. So you see that the flow separates earlier on the smooth side, whereas on the rough side, the flow separates later. And it's this asymmetry which causes the side force, which then eventually results in swing. Okay. Now, in a physics-based modeling, what you would like to do, let's say you want to predict the swing of a cricket ball, right? What you would do is to really get to the physics of the problem. Right? So if you notice, right, I mean, there are many bowlers who have preferences who don't want to bowl with a new ball. They want probably an older ball, or you would often see them scratching the ball on their body, not because they have an itch, but probably because they want to make one of the sides rough, so that you can take advantage of this very nice fluid dynamics effect, right? So if you're doing a physics-based modeling of understanding how this cricket ball swings, then what you would like to do is to really get down to the fluid flow, the details of the fluid flow. What is the nature of the laminar flow here? What is the nature of the turbulent flow, and what is the nature of that interaction which gives rise to these forces, and so on. You would do a detailed study, and that's a very domain-specific problem that involves a lot of expertise in fluid dynamics, in high performance computing perhaps, or in experimental aerodynamics, etc. Right? On the other hand, you can have an entirely data-based approach, which doesn't really require you to have a lot of detailed understanding of the physics. For instance, you could do a bunch of experiments or high fidelity numerical simulations, which would give you a bunch of data points. And you could say, you know what, I may not know the entire physics about the problem. I don't know exactly what happens, but I have this experimental data which tells me how the, let's say, the pressure is distributed around the ball, and that allows me to go ahead, use this as some information that is given to me that I implicitly trust, and use that going forward to make some inference about the swing of a cricket ball. Okay. Now, in database modeling, you often like to work directly with the data, whereas in physics-based modeling, you look into the details of the problem, and each have their own pros and cons. Okay. In database modeling, the advantage is that you don't really need to know a lot about the physics. You can directly get on with the data and begin to make some inferences. But that precisely is its disadvantage, because anyone can make a statement, right? You don't really need to know anything about the subject, and you can still make some statements about it. It's a real problem, actually. On the other hand, with physics-based modeling, right? So there is often a limitation on how much we can model. Okay, there is a lot about turbulence, for instance, which we don't understand. It's one of the classic open problems in physics, and so we don't understand everything, and therefore we are forced to make approximations. Okay, so even though you have a lot of domain knowledge, you're forced to work with approximations. So there are pros and cons to both these approaches. I mean, physics-based modeling is more meaningful, and it's more provides you with a lot of insight, but it's much more difficult, and it also requires a lot of domain expertise. Whereas database modeling is relatively simple, but it does not give you as much insight as a physics-based model would do. Okay? And a lot of what I'm going to be doing today, talking about, is whether you can, in some ways, have the best of both worlds, right? Can you take what is best about database approaches and what is best about physics-based approaches, and put them together and see if something comes out. Okay, and that's the whole idea of physics-based modeling. Okay, in short, that's what we would be studying. Again, I won't be focusing on the details of this particular example, as fascinating as it is, but we will rather be looking at much simpler examples. This was just to motivate the setup. Okay, and here is a larger view of how it all fits together, right? So what you want to do is, once you have a physical problem that you want to study, let's say the swing of a cricket ball or anything else it fancies that gets your attention, you restate that physical problem as an optimization problem, where you say that you want to penalize violations of that, the known physics about the problem. Okay? The moment you penalize violations of the physics, that automatically has an optimization structure, because what you want is a setup that satisfies the physics in the best possible way, or which gets the physics wrong in the least intrusive way. You can think about it in multiple ways. Okay. Now, what really makes it interesting is that you can use a very interesting idea called as differentiable programming, where you can, in principle, study how your solver itself would vary if you change various aspects of your solver. Let's say you have an optimization problem. You can differentiate through the entire problem. Okay, and this is something that will be a constant theme of our of this presentation, and you will begin to see the advantage of having a differentiable programming approach by the end of it, hopefully. Okay, and what is going to be a key player in differentiable programming is this notion of automatic differentiation. And I'm not sure how many of you have had an introduction to automatic differentiation, so I'll provide a reasonably detailed introduction. The idea is that it allows you to calculate the gradients of various functions automatically. Okay? And the gradients are at the heart of optimization, as should be evident by now from this workshop. And the idea in physics-based model, in differentiable programming or differentiable physics or this physics-based learning, is that you're going to differentiate through a solver. Okay, so you're going to combine traditional machine learning and these very fancy differentiable programming where you can differentiate through a solver, and you put that together in the context of a physical problem, and you can really begin to draw newer insights that you would have otherwise missed. Okay, good. Now, this is a very large problem. I mean, there's a significant amount of research that is happening currently in this area in differentiable physics. So it would be difficult in an introductory workshop such as this to cover all the details. Okay, so rather my intention is to provide you with a very simple and minimal introduction to what differentiable physics is all about, what this differentiable programming is, and hopefully that will whet your appetite to dig further and learn more about this. Okay, so that's the thing. Now, I'll do a very quick review of optimization, and most of this should be familiar to you by now because you have already sat through many lectures which have gone through this in painful detail. So I will not take too much of your time in going through the basics. So I'd rather go through it in a slightly fast-paced manner. The notation might be new to some of you. This is more mathematical notation than what is typically used in this workshop, but it's okay. It's not. It just looks different, but it's not any more difficult. It's pretty straightforward. Anyway, so the idea in basic unconstrained optimization is that if you're given an objective function which takes n real variables to a single real variable, we will deal only with continuous optimization. Then you want to find a minimizer of that particular function, objective function, right? So that's mathematically written like this, where you want to find the argmin. This simply means that you want to find the argument x, which minimizes this objective function f. So when this could be a set because you could have multiple minimizers for a given problem. Imagine a two-well potential that naturally has two minima. Or in general, if you look at realistic landscapes of objective functions you meet in practice, you would have lots and lots of local minima. Okay, so this is in general a set, which is why you have an inclusion operator here. It's not x star equal to argmin f; it's x star in argmin f. Okay. Now, if your objective function is nice enough to admit derivatives, then you can come up with conditions that a minimizer has to satisfy. Okay. So the first order necessary condition tells you simply that if you have an optimal point, the gradient of the objective function at that optimal point has to vanish. Okay, notice that the implication is one way, it's not the other way around. The reverse implication is in general not true. For instance, you can have a saddle point. Okay, a second order sufficient condition for a minimizer is that the Hessian of the objective function at the point x star, which is your solution candidate, is strictly positive definite. Okay, I presume all of you know what strictly positive definiteness means. If not, let me know and I can explain. So if you have this condition which is guaranteed, then you can be assured that x star is indeed a local minimizer of your objective function. Okay, this is the very basics of unconstrained optimization. And of course, you can also apply these optimization algorithms to cases where f is not differentiable, but you would no longer have these kind of nice conditions. Okay, that you would have to either suitably relax them, or you would have to come up with heuristic methods to solve them. Okay, we will not be worrying about those details here. Now, in general, you would have to use a numerical technique to compute the minimizer. And the class of numerical methods that I'll be talking about are what are called as iterative algorithms. Okay, in particular, the gradient descent algorithm. The larger idea behind a gradient descent algorithm is that you would be constructing a sequence x1, x2, x3, and so on, such that the limit of that sequence gives you a minimizer. Okay, that's the whole idea behind an iterative scheme. And there are multiple ways in which you can construct such a sequence. The simplest possible approach, the simplest possibility, of course, is to use what is called as the gradient descent algorithm. And we have already seen this as part of this workshop earlier. So people talked about, for instance, the steepest descent algorithm. That's exactly the same as what I'm calling as gradient descent here. And the idea behind the gradient descent algorithm is that if you look at any particular iterate xn, then the direction at which the function changes most rapidly is given by the gradient of f, the objective function at that particular point, at that particular iterate. And therefore, if you move in a direction opposite to the gradient, you're guaranteed to reduce the objective function. Okay, that's as simple as that. So you have this very simple iteration scheme where a successive iterate is computed from a previous iterate by moving in a direction away from the direction of the gradient. Okay? And this particular constant alpha n that you see here is what is typically called as a step size, or in the context of machine learning, the learning rate. Okay. Now, machine learning uses a lot of ideas from optimization, and I think it's at some level it's fair to say that it's just applied optimization. Okay, there's nothing fundamentally new in that. So people just come up with new names for very old ideas. So don't be surprised to see the same ideas repeating there. So alpha n is just the step size in classical optimization, but it's called as a learning rate in machine learning. And the nice thing about the gradient descent algorithm, and this is something that the speaker earlier today also emphasized, Professor Mahajan, that it's guaranteed to converge, right? So you're guaranteed to converge to a local minimizer of your objective function if you choose a step size properly. That's one of the nice things about the gradient descent algorithm. Good. Now, again, I thought, why not use a function that you've already seen? So Professor Pant showed some very nice examples of finding the minima of the Himmelblau function yesterday using simulated annealing. So I thought, why not? I'll just show you how it works in the context of a gradient descent algorithm. Okay. Now, here is the Himmelblau function that you've been seeing throughout the workshop. This is how it looks like, the surface plot of that. And here is a contour plot of the same thing. So you see that it has a local maxima, which is given by this yellow dot. And it has 4 minima, local minima, which are these red stars. Okay. Now the goal is to find these minima numerically. You already have seen an example of how to do that using simulated annealing from Professor Pant's lectures. What I would be instead doing is to show you how it looks like from a gradient descent point of view. So what I've done here is to choose 4 different starting points, all of them close to the local maxima. Okay? I'm not sure if it's okay. Let me just zoom out. Okay. So you see here that this yellow dot here is the local maxima. So this white dot that you see here is the starting point. So if I start at this point, you see that the gradient descent algorithm, successive iterations of the gradient descent algorithm, take you towards this global minimum. And you see that the path that it takes is not just a straight line or something. It actually goes on the contour. So you see that dark blue means it's really low, and towards red it gets higher and higher. So you see that there are very high values of the function here. So this is a local hill here, and it flows down the hill, but it takes this path and goes to this red point. But what if instead I start at a neighboring point around this blue thing? So you see here that instead of starting at the top, right, I'm starting at this point. You see that it converges to a different minimizer, but along a different path. And you can do the same thing if I start with a point on the northwest, it converges to this particular point. And if I start with a point on the southwest, you end up at a different point, different local minimizer. Okay? So the point of this is to show that the gradient descent algorithm is sensitive to the choice of the initial condition, right? So depending on the choice of the initial condition, you could converge to different local minimizers. And there is a way to make this precise using the notion of what is called as the Basin of Attraction. So typically, if you have, if you collect together, let's say all the points, all the starting points, which would end up in this particular local minimum when you run the gradient descent algorithm, that is the Basin of Attraction for this local minimizer, and so on. So you can partition the input space into technically a union of these basins of attraction. Of course, you would have special points where nothing could happen. For instance, if you start exactly at the local maximum, okay, it could in principle just stay there and not move at all, because the gradient is zero. It would forever stay there, so it would not be part of any of the basins of attraction. But that's most points would be covered in the during of these basins of attraction. Good. Now that is very simple stuff, and by now you should have seen lots and lots of examples of that as part of this workshop. So I want to emphasize more on that. I also want to talk very quickly about equality constraint optimization, because we would need some of these ideas later on. And here the idea is that instead of minimizing the function, objective function, over the entire space Rn, you want to minimize it over a subset of Rn. Okay? So if you recollect our definition of constraint optimization, you see that the design variable, the optimization variable x, is free to roam around all of Rn. And that's why it's unconstrained. There's pretty much no constraint on where x can be. Whereas if you look at the current situation, x cannot move anywhere it wants in Rn, but it's constrained to stay inside the set K, right? And that's why it's called as constraint optimization. And if the set K is obtained as a consequence of a bunch of equality constraints, so if it is, for instance, a set of all points which where these these m functions g1, g2, etc. up to gm are simultaneously equal to 0, that is an example of a set which is defined entirely by means of equality constraints. And an optimization problem where you seek a minimizer of an objective function subject to equality constraints is what is called as an equality constraint optimization problem. Again, this is something that you've also seen before in the workshop. The idea to solve this is actually quite simple. So the trick is to transform this constraint optimization problem into an unconstrained optimization problem, because you know how to do that. Gradient descent is simple and beautiful, works really well. So how do you convert this constrained optimization problem into an unconstrained problem? That's the essential question, the key question. Now, there is a very beautiful mathematical theory that lets you accomplish this by introducing what is called as the Lagrangian. Unfortunately, I will not have the time to get into the details of this theory in this talk, but there are tons of excellent references, some of which were presented earlier, and where you could find those details. Okay. Now, the idea is very simple. So you extend the space Rn into the Cartesian product of Rn and Rm, which and introduce this function called the Lagrangian, okay, that takes as its input not just the point x, which are the design variables, but also a bunch of constants called as the Lagrange multipliers. Okay, these are just parameters in another n-dimensional space. And you construct this particular Lagrangian as the sum of the objective function and a linear combination of your equality constraints. Now, what can be shown is that once you have this kind of a Lagrangian, your original constrained optimization problem can be shown to be an unconstrained optimization problem for the Lagrangian. In particular, it is what is called as a saddle point problem. If you look at this function L as a function of x while keeping lambda fixed, then the minimizer with respect to x is what you seek, or equivalently, if you fix x, you want to find the maximum with respect to lambda. Okay, these are two different ways of looking at the same problem. But if you look at that saddle point, which is given by this condition, okay, a necessary condition for a point x star comma lambda star to be a saddle point of this Lagrangian is if the gradient of that particular objective of this Lagrangian, sorry, this is a typo here. This should be L, okay, not F. This should be L. I'll correct it and upload the new slides later on. So sorry about that. So if you have the gradient of the Lagrangian with respect to x, if you have an optimal point x star lambda star, then the gradient of the Lagrangian with respect to both x and lambda would vanish at that saddle point. Okay, and that's the criterion. But in practice, right? So what we will use is a much simpler version of this algorithm, what is called as the what is called as the penalty method for equality constraint optimization. Now, you can think about the penalty method as the poor man's version of an optimization algorithm. It's a simple and brain-dead idea, but it really gets the job done. So the idea is very simple. Suppose that you want to minimize an objective function f subject to an equality constraint g of x equal to 0. Right? Now you convert that to an unconstrained optimization problem by adding a penalty term. And if you look at this penalty term, it has a structure of a constant multiplied by this squared norm of the equality constraint. Now, whenever you have g of x taking a value outside 0, anything other than 0, this is going to be strictly positive. So it raises the value of the entire objective function, and therefore any point which violates this equality constraint can no longer be a minimum. Okay? So what you're essentially doing is that you're penalizing any kind of a deviation from the equality constraint. And that gives rise to this augmented form, right? So you have the objective function plus a constant times the square of the constraint. Now, if you take this epsilon parameter to go to 0, or in other words, the constant becomes larger and larger, then you see that there is way more penalty to deviating from the set g of x equal to 0. So what this term essentially does is, when you run your unconstrained optimization problem on this joint function, f of x plus 1 over epsilon norm g whole squared, it naturally makes sure that your iterates are staying in regions which have low values of g. That's exactly what you want. And in the limit when epsilon goes to 0, this term gets really, really big if your g gets away from 0. Okay, so this automatically forces your iterates to stay on the set g of x equal to 0, which is exactly your constraint set k. So if you look at the set where g is 0, that is precisely your constraint set k. So instead of explicitly enforcing the, requiring the iterates to stay in the set k, you impose a soft constraint. So this is an example of a soft constraint, because it's still possible for x to stay outside. It would just incur a large penalty, not an infinite penalty, just a strong penalty. And therefore, you see that this particular form of a constraint optimization problem gives you a way to compute the necessary optimizer, the necessary minimizer. And you can show that in the limit when epsilon goes to 0, this actually approaches the true minimizer of the constraint optimization problem. Okay? Now, this is a very standard strategy. It's a very simple idea, but it's not always the best thing to do. The reason is that it can be very sensitive to the choice of epsilon. And as epsilon goes to 0, you see that this term becomes very large. And especially if you take the gradients will become very large. And if you have done any kind of numerical work in gradient-based optimization, you know that when gradients start blowing up, you're going to end up in all kinds of problems. Okay, so even though this is conceptually very neat and very easy to understand and has this nice theoretical property, in practice, it's not always the best idea. And often we don't have a very good handle on how to choose epsilon, how small should epsilon be. Okay, so these are practical limitations. There are much better algorithms for equality constraint optimization. But for our purposes, this is an introductory workshop, and we want to just have something to play around with. So this is good enough. Okay. Now, with that, I think this will be a natural segue to get into automatic differentiation. So I'm going to pause. I'm going to violate my own statement earlier. I'm going to pause for a brief minute and see if there are any comments or questions. So I don't see any comments. Okay. I'm going to have a sip of water and give you time to think about what is happening. So if there's nothing that you would like to share, then I'll proceed. Okay. Oh, by the way, how many participants are there right now? Just out of curiosity. Oh, there are 17. Oh, but that means probably 16. That's good. That's a decent number. Okay, good. So the what I covered until this point is a very quick review of optimization theory. Okay, and of course, if you're coming to optimization completely without any background, that would have been a very fast introduction. But hopefully, after the 4 days of workshop, you have by now seen that those ideas quite often, and therefore it should have not been, hopefully not too fast. But one idea which is making a lot of buzz these days is automatic differentiation. And the idea here is that if you want to compute the gradients of objective functions, which is what you need. So if you look at the gradient descent algorithm, right? So what is happening is you move away from a current iterate, right, in the direction of the negative gradient. But this gradient term features heavily, right? So that's central to the gradient algorithm. And how do you compute this gradient, right? There are many ways to compute the gradient in practice. So you could simply use numerical differentiation, right? If you would have seen about simple finite differences, if I want to compute, let's say, the derivative of a function f of x numerically, you could look at f of x plus h, where h is small, f of x, and look at the difference of f of x plus h minus f of x, divide that by h. The limit will give you the derivative. That can be used to find the derivative, simple finite differencing. And that's an example of numerical differentiation. Or you could do symbolic differentiation in case the function is simple enough that you can actually hand calculate the derivative, or you can use a symbolic manipulation package like Maple or Mathematica, whatever, to compute the derivative. You can do that, but that's kind of limited. You can only do so much. A very powerful tool in this setting is automatic differentiation. Okay, and again, I want to emphasize that these ideas are very, very old. Okay, automatic differentiation has been around for at least 3 decades now, but people are now very excited about it because of the craze behind machine learning. But these ideas are actually quite old. Now, automatic differentiation is a very nice idea, which allows you to calculate exact derivatives at the points where you're querying. So if I give you a function and I want to compute the derivative of the function at a particular point, you can compute that pretty much without any numerical error using automatic differentiation. And that's what we will study, okay? And this is also called as algorithmic differentiation, and comes in two major flavors, okay, which are the forward mode and reverse mode automatic differentiation. We will very quickly look at both of these now, okay? First of all, what is to understand automatic differentiation? It helps to think about how functions are represented, can be represented, and how does a typical evaluation of a function happen. Let's consider a simple function of two variables, x and y, which takes x and y, f takes x and y, and gives you xy plus the exponential of x plus y. Okay, so suppose I want to compute this. Now I can express this in a graphical form in this way. Okay? So on the left end, you see that there are two input variables, x and y, and you see that there are a bunch of simple operations, multiplication, addition, exponentiation, addition, which when appropriately composed give you the final function f of x comma y. Okay? For instance, suppose that I call this xy as the variable a, and this function, this quantity exponential of x plus y as the variable c. So you see that your function f is nothing but a plus c. Right, so that's what I'm writing here. So you see that the function value which I represent by z is nothing but a plus c. So z is obtained as the addition of the variables a and c. What about a? A is just this function x times y. So you see that a is the product of x and y. Of course, x and y are the root variables. They do not depend on anything else. They are the independent variables of your function. Right? So similarly, if you look at this function exponential of x plus y, it is obtained by acting the exponential function on this quantity x plus y. Let me call that as b. So if b is x plus y, then this quantity that you see here, which is our c, is nothing but the exponential of x plus y. And x plus y in turn is nothing but the addition plus operator acting on x and y. So you see that there is a very systematic way in which you can decompose any complicated function into a composition of elementary functions. And by elementary functions, I mean addition, multiplication, division, subtraction, sine, the trigonometric functions, the logarithmic functions, etc., which you all know how to work with very well, which is something that we often use in our studies, right? So a complicated function can be broken down into a composition of elementary operations. And this kind of a representation is what is called as the computational graph of the function. And once you understand how to express a function in terms of its computational graph, it's kind of straightforward to differentiate the entire thing, because all you have to do is to follow the chain rule of differentiation. I presume all of you are calculus experts and you remember your chain rule of differentiation. So if you look at each of these functions, right, individual functions, multiplication, addition, exponentiation, These are very simple functions. You know how to take the derivative of these functions. So if you use the chain rule, then what you can do is to just compose together these derivatives, and that automatically gives you the derivative of the total function. That's the whole idea behind automatic differentiation. And central to that is this idea of expressing a function as a computational graph. Okay. Now, so this is what I said. So if you look at this particular, let's focus on this operation, a equals x times y. If I take the derivative of a with respect to x, I get y, right? So that's what I'm writing here. So this node a, if I take the derivative of that with respect to this leaf variable x, what you end up with is y. So this is something that you can calculate because it's a very elementary operation. So you know how to compute the derivative. Similarly, if I look at the derivative of a with respect to y, I end up with x. So I can store that in this edge of this computational graph. And similarly for each of these elementary operations, for instance, if I focus on this particular edge, so you see that this c is obtained as exponential of b. And how do you compute the derivative of the exponential? It gives you back the same exponential. So the value stored on this edge is just c. So in this way, you can compute the value of the derivative at each of these edges. And each of this is a very simple calculation. For instance, if you look at the quantity z, that depends only on a and c through an addition operation. So if you take the derivative of z with respect to a, you just get 1. Take the derivative of z with respect to c, you get 1. Okay? So you see that you don't have to worry about the derivative of z with respect to x, which is what we ultimately want. But you're just focusing on locally, if a particular variable depends on some other variables, how does that derivative work? And that depends entirely on the local function here, which is an elementary function and which is very easy to differentiate. It's a simple idea that automatic differentiation takes advantage of. So in forward mode AD, what you do is you use this information, use these nodal values of the derivatives to propagate the derivative from the independent variables to the final variable. So suppose I want to compute the partial derivative of f with respect to x, okay? Then what I can do is to set a seed variable for x, which I call as x dot, to be 1, and a seed variable for y to be 0. And then all you have to do is to just multiply this towards the right. It's just this chain rule of differentiation if you sit down and work out the math. So you see that if I want to look at this particular node, it has two arrows coming into it, one an edge with weight y and an edge with weight x. The edge with weight y multiplies the seed 1. So it's going to be 1 times y plus 0 times x. Okay. And similarly, if you look at this particular node, this plus function has two edges coming into it, right? So this has weight 1 and this has weight 1. So 1 multiplied by the seed value 1 is just 1, whereas 1 multiplied by the seed value 0 is just 0. So 1 plus 0 is 0. So you see that here. In an analogous, sorry, in an entirely analogous manner, right? So you can propagate this derivative from the left-hand side to the right-hand side. And all you have to do is to multiply the seed value which by the appropriate weight of the connecting edge and push it forward. For instance, here the seed value becomes a dot, which is just y here, because it was y times 1 plus x times 0, which is just y. So you just use this y value to multiply it with the corresponding edge here, which is 1, and that's sent here. And similarly, you can do for the other edges also. And when you do this, the beauty of this particular process is that when you do this kind of a propagation, forward propagation of these derivatives from the input variables all the way to the output, you end up with a partial derivative. The final seed value that you get here is the z dot, is nothing but the partial derivative of f with respect to x. Okay, and this is not magic at all. It's very, very straightforward. This is exactly what you study as the chain rule of differentiation in undergraduate calculus. Okay. On the other hand, if you want to get the derivative of f with respect to y, then all you have to do is switch these two. Set x dot equal to 0 and y dot equal to 1. Do the same process, and then you would end up with the partial derivative of f with respect to y. Okay, so I would leave that as an exercise for you to work with. It's a good idea to put pen to paper and figure out the details. As I said, these slides are freely available online. I've given the link also So feel free to have a look at this, sit down, and make sure that you understand the details. Okay, it's a very simple idea. The larger point I want you to understand is that if I want to compute the derivatives of this function, right, this depends on two variables. It's a scalar valued function of two variables, so it will have two partial derivatives. If you want to compute these two partial derivatives, you have to scan this function computational graph twice. Once to compute the partial derivative with respect to x, and a second time to compute the partial derivative with respect to y. If you have a function which depends on a lot of variables, this is a problem. Let's say you have a function which depends on thousands of variables, which is not uncommon in modern optimization. Then to compute its derivatives, you have to, in some sense, uh, run to evaluate that function 1,000 times, however number of variables that you have. Sorry. You need to evaluate it for that many times to get all the partial derivatives. So that is one of the disadvantages of the forward mode algorithm, automatic differentiation algorithm, even though it's conceptually quite simple. Excuse me. Yeah, something's up in my throat. So there is a way to get around this difficulty, which is using what is called as a reverse mode automatic differentiation. And in many ways, it's this algorithm which is kind of powering a lot of the machine learning libraries today. And again, this idea is not new at all. Okay, this has been around for a very long time. And in fact, in structural mechanics, this is called as the adjoint method in topology optimization or structural optimization. Same thing goes under different names in different disciplines. It's called as back propagation in the context of neural networks. It's the same as so. Yesterday we had Professor Hota talking about the Pontryagin principle and the optimal control problem. There, if you look at the 2-point boundary value problem that you get, the reverse problem is again an instance of this kind of an algorithm. Okay, so the same idea gets repeated in multiple disciplines, and it's called by different names in different disciplines. But then sometimes people get very excited with depending on how you call it. Maybe if I call it as the adjoint method, no one would blink an eyelid. But if I tell that it is back propagation, then suddenly the whole world is interested, right? So it's the power of marketing, I suppose. But in any case, we can. The idea here is again exactly the same as before, right? It's simple composition of functions and the chain rule of differentiation, except that you don't start with seed values like in the forward mode automatic differentiation, but rather you start at the output z. Now suppose that I have a function L that depends on z, and I want to compute the derivative of L with respect to x and y. Now what I'm going to do that is to reduce the problem to computing the derivative of L with respect to its immediate variable, which is z. So I'll just compute the derivative of L with respect to z, and eventually we will set this quantity to be 1. In other words, L is just the identity function. Okay. Now, the whole idea here is again to use the chain rule of differentiation, and the intuition is that if you want L to change, L depends on z. Okay, so the way L can change is depends on how z can change. And how can z change? Z can change either because of a change in A or a change in C. So if you know how z varies with respect to A, which is great, which is you know that information, and how z varies with respect to C, that is also something you know, then you can back propagate this information to the previous layer. Okay, so that's why you see that the direction of the arrow is backward. You're going from the output to the input. So initially you start with a seed value of 1 on the right hand side, and now after one iteration, what you see is that you have gone back here. So you can now compute how L changes if I change A. And with a simple chain rule of calculus, you see that it's nothing but how L changes with respect to Z times how Z changes with respect to A. Now, how L changes with respect to Z is your seed value 1. How Z changes with respect to A is nothing but your edge weight, which is again 1. So the product of these two is 1. Similarly, if you want to compute how L changes with respect to C, you can combine how L changes with respect to Z and how Z changes with respect to C. And this combination is going to tell you how L changes with respect to C. You can keep doing this again, step by step, and now you can look at how L changes with respect to X. which is ultimately what you want. Okay? Now, if you carry out this algorithm, there's a simple idea of finding out which depends on what, and then computing the corresponding weights and back propagate the weights along this computational graph. What you end up with in the initial layer are precisely the partial derivatives of your function. Okay. Now, if you choose L to be the identity function, then Z is nothing but your function f of x comma y, and therefore the partial derivative of L with respect to x is nothing but the partial derivative of f with respect to x, and likewise the partial derivative of f with respect to y. So you see that by following this simple rule, by very cleverly manipulating the derivatives and how that information is carried out, you can actually compute the gradients of any function that you want. Now, unlike the forward mode automatic differentiation, in the reverse mode, you get all the gradients in one sweep. So again, you should put pen to paper to see how this actually works. And I would strongly encourage you to do that. Please look at this slide again. Try to work out the details and try to see how exactly you get all the gradient information in one sweep. Okay? Because the best way to understand it is to actually hand calculate it and see how it works in the context of a particular application. And when you do that, what you would see is that the in one sweep, by just evaluating the function, you can compute all its partial derivatives. Okay, so if I have a function of a scalar variable that depends on two, let's say, independent variables, then the derivative of this objective function with respect to these input variables can be calculated in just one sweep. Okay, but that's the real advantage. So if I have a function which depends on thousands of parameters, you don't need to evaluate the function thousands of times as you did in the context of forward mode automatic differentiation, but just a single evaluation would give you all the derivatives. Okay, so that's the power of reverse mode automatic differentiation, and that's the reason why it is so powerful. Okay, and again, as I said, this idea is not new. It's been used for a very long time under different names, but in its most modern reincarnation, it is called as the back propagation or reverse mode AD. Okay. Okay. Now, when would you want to choose either of these algorithms? Okay, so if you want to compute the derivative of a function, the partial derivatives of a function which has this signature, which is a function which takes Rm to Rn, so it takes m real numbers and gives you n real numbers, then you want to use the forward mode if your number of independent variables is much smaller than the number of output variables. So because the number of times you want to run the forward mode here is m. Whereas if you want to use a reverse, if you have a situation where n is much smaller than m, or m is much larger than n, then you would want to use the reverse mode. That's the more expedient thing to do. And in most cases in optimization, you will have this situation where the number of design variables is going to be much larger than the dimensionality of the objective function, the output of the objective function. Okay, and that's the reason why reverse mode AD is so much more powerful. Now, there are many ways to implement automatic differentiation. It's a fascinating subject by itself. Now, there are two primary ways to do that in practice. You could do what is called as a source-to-source transformation. Okay. Or you could employ what is called as operator overloading. Unfortunately, I will not have the time to get into the details of all these implementation details here. But what they do is just a clever variant of what you're seeing in these two pictures. But it's done in depending on the language or depending on the situation at hand, you might want to prefer one over the other. Okay? Now, the nice thing for us now is that because of all the craze for machine learning, you have really high quality software to do this for you. You don't need to actually understand the precise details of the implementation, though I would encourage you to understand it. Okay? It's a good idea to know why it happens, how it works, but you don't have to sit and write everything down. It's all done for you. And what I'll show as part of this workshop is how this is done using a very nice package called Pytorch. Okay, so Pytorch is an open source package for machine learning, particularly neural networks that I'll be using as part of this workshop. And what I'll do is I'll illustrate how this forward mode AD works in the context of using Pytorch or reverse mode AD, sorry, not forward mode, reverse mode AD. Good. So what I'm going to do now is to switch to a hands-on session. Okay. The original plan was to have 1.5 hours of lectures and then a hands-on session for 1.5 hours. But rather, what I've decided to do is to have a single session for 3 hours with lots of breaks and with hands-on and presentation going back and forth. Akshay, is that okay? Okay, so what we'll do is it's about 3:20 now, so it's less than an hour. So let's do a quick hands-on session, and then we can probably take a small 2-minute break and then come back and then continue. Okay. At least for this, I think it'll be good if you can follow along with you can write the code yourself and see how it works, because that would give you at least a hands-on perspective of how Python works. Okay. Now, since a lot of you don't have a prior background in Python, what I'll do is I'll probably run you through some very basics of Python very quickly. Okay. This is not intended to be a tutorial on Python, but just to give you some very basic information that'll help you get started. Okay, so make sure that you're able to you're in this page. So I've given the instructions earlier. So if you go back to the chat window, please go to this link, https://collab.research.google.com. Okay, so this is a cloud-based Python notebook interface, which is very convenient for working. You don't need to install Python or anything. Yeah, Harish says please resend. It's right here. Okay, do you see this here? It's collab.research.google.com. This link, the first link. So if you click on that, it will take you to if you have a Google account, you automatically have access to that, free access to Google server with both CPU and GPU present, so you can play around with that. So please click this link. It will take you to a place where it will give you a prompt. Click on the new notebook prompt there, and you will end up with a screen like this. Okay, so I'm just going to give you a couple of minutes while I take some water while you set it up. Okay, so is anyone having problems with this?
No, sir.
Okay, good. Okay, let's get started right away. So Python is an interpreted language, which means that you can see the results of your commands as soon as you type them. It's similar to what you do in MATLAB. You can also write a script, which you can then run as a from the command line or whatever your favorite IDE is. So let's start with a very simple thing. So 1 + 1, and to execute this, you have to press Shift and Enter simultaneously. So press Shift, and while you're holding Shift, press Enter. If that doesn't work, click on this arrow button on the left. Okay. Now, if you have Python installed in your machine, this will happen in a blazing speed. But because you're running it on the cloud, what is actually happening is that this information is sent to Google, and Google is evaluating it for you and sending it back to you. So it's running Python in a server which is somewhere in the world. So that's the reason why you would see a small delay. But you see that you automatically see this output, and you can initialize variables like this. So say a is 1.2, sets the variable a to 1.2. Let's say b is 2.4. And if I want to multiply a and b, I can just do a star b. So let me do c is a star b, and let me print c, and then press Shift Enter, and you will see that this is the product of a and b. 1.2 times 2.4 is what you get here. So it's very simple to initialize variables. So you see the output immediately here too. And an important that you want to know is how to work with functions. Right? In Python, the way you define a function is using the def command. Okay, it's short for define. So def is just saying that you define a function. So let's say sqr, it's a square function which takes input x, and you put a semicolon at the end of it. Okay, that tells you that this is the function name, this is the argument that the function takes. And in Python, the way you tell that the following piece of code is the body of the function is by indentation. Okay, indentation means that the code is going to be shifted to the right by a specific amount. So you'll see that this particular editor automatically does that for you. Okay, so Python understands scope, variable scope by indentation. That's a very unique idea. It was introduced in Python, and now it has become kind of its signature things. Okay? So what you do is you say return. So when you evaluate this function, you want to return x star x. Okay, so if I have this particular function, then you have defined this function. You see the tick mark over on the left hand side, which tells you that this function has been defined. So if I want to calculate the square of any quantity, all I have to do is sqr of, let's say, 2 and press shift enter, and you should automatically see 4. And the nice thing about Python, unlike languages like C or Fortran, is that you don't need to define the variables. X can be anything. It need not be. You don't need to define it as an integer or as a a floating point or complex number, etc. So for instance, I can do something like sqr of 2.2, and if you press shift enter, it should give you 4.84. That's exactly what you see here. So it works on that. It also works with complex numbers. So if you have 1 plus 2j, this stands for the complex number 1 plus 2i. In Python, it's 1 plus 2j. So if you press shift enter, it will give you the square of that particular complex number. So you see that you wrote a simple function, but then you're able to apply it to objects of very different types. And let me see if this works. If you just give it a string, this will not work, okay, because the star operation is not applicable to the an object of the type string. So it's not that it applies to every operator, but any compatible type. If you cannot give it a character and expect it to work, but if you give it any other number, right, so it should technically work. Right? So this is a very, you see that it has a very simple structure. The language is not very difficult. And if you want to do a loop, okay, so for instance, suppose I want to do a simple for loop. So let's say for, if you want to print the first 5 numbers, 1 to 5, then the way you would do it is for I in, the English word in, the range of 5. Okay, this would give you what is called as an iterable object, which will give you the numbers from 0 to 4. Okay? 5 is not included. Then you can just say print I and press shift enter, and you will see that it automatically prints the variables for you. And if you want to have, let's say, a if else condition, okay, so let's say you can, by the way, we already defined a as 1.2, I can redefine it to be whatever I want. So suppose I define a to be 3.141516, and then if I can do something like if a is greater than 2, print greater than 2. Yeah, and you see that it automatically prints that. I didn't mean to press shift enter, I just wanted to press enter, but it's okay. And the way you would, if you want to change this, you can go back to that link cell, and then you can say else. It tells you what happens if this is not satisfied. Then print less than or equal to 2. But of course, the output here would be the same because a is indeed greater than 2. Right. So this is a very simple, and the other condition is, of course, else if is not there in Python. It's called elif. ELIF. So you can have whatever condition that you want. Don't forget the trailing colon. Okay, that's the simple thing. By the way, when you're writing something in Colab, this is technically in what is called as a Jupyter notebook format. You can also add text here. For instance, if you forward your cursor on top of this, you should see these two blocks. If you press text, it changes into a text box, and I can write whatever text I want. uh, in any fancy format too. So I can have, for instance, I can make this a bold format, and the way you would do it is with the double star. And the nice thing about Colab is also that you see the corresponding, what you would get as the output on the right hand side. And again, to evaluate this, you just press enter. So you see that this is a nice format to create content. If you want to create an interactive set of notes with code, this is a very nice way to do it. There are tons of very nice textbooks also written like this, so please feel free to check out Jupyter Notebooks, and this can be a very interactive way to teach too. Okay, so again, because we are in a session where we want to really look at physics-based learning, I do not want to spend too much time on you know teaching Python. It's unfortunate that most of you don't have a background in Python, but it's okay. It's an easy language to pick up, so I'm pretty sure if you spend a couple of days, you should be able to understand the language pretty well. Okay. But let's try to look at least automatic differentiation in a hands-on way so that you know how to do it, and then we can see about the rest. Now, there are a lot of functionalities which are provided in Python with the help of libraries. Okay, before I do that, let me quickly check if there are any questions. It's here. No questions? Okay, good. Okay, so the way you would import new functionality in Python is by importing libraries. Okay, and the simple way to do that is using the import function. Okay? This allows you to import packages which are domain specific. Okay, for instance, you can have an package especially for optimization or for plotting or for machine learning or whatever. You import them using this import command. And there are three packages that we will require as part of this particular workshop. Okay? So the first is the Numpy package. Okay? What Numpy does is it stands for numerical Python. It collects together a lot of nice array-based functionalities that you would require when you're writing numerical code. The second thing is you want to plot whatever you're doing. So a very useful thing is what is called as matplotlib. So from matplotlib, which is a very big library, you just need to import one particular module, which is called as pyplot. Pyplot is a very handy package to plot graphs, etc., 2D graphs. And finally, for our automatic differentiation, we need to import Pytorch. And the way you do that is by writing import torch. Okay. And once you do all this, press Shift and Enter. It will take a couple of seconds to import these packages. But once they're imported, you should see a green arrow on the left. Sorry, a green tick mark on the left. And that would tell you that these are imported successfully. Okay. Good. So I presume all of you are with me until this point. Is anyone not able to do this until now? I mean, is anyone not able to do this? Input 14. How do I go there? Yeah. Okay, good. Okay, now let me first show you how to plot using pyplot, and then we will get into automatic differentiation. So suppose I want to plot the function sin x over the interval 0 to 2 pi. Okay, the way you would do that is to first create a bunch of x values from 0 to 2 pi, and NumPy gives you this very nice feature called linspace. Okay, NumPy dot linspace. So in Python, the idiom is that if you want to use a function belonging to a package, then you just use the package name dot the function name. And the nice thing about this editor is that it automatically tells you what that function's arguments should be and what the help is. Okay, so it tells you, in particular, if I type linspace, it tells you that you have to have a start argument, a stop argument, and then some optional arguments. And then it also tells you what it does. It gives you a brief description, and it also gives you some examples of how to work with it. Okay, so it's a very handy feature, and in general, Python is built around ease of use, so it's very easy to learn, very easy to use. So what I'm going to do is I'm going to create points between 0 and 2 pi. So pi is not a named variable in Python. You have to define it from NumPy or the math module. And let's say I have 50 points between 0 and 2 pi. So let's see what this looks like. So if you print this s variable, you see that it is an array, it's an object of type array, and it has values between 0 and 2 pi. This quantity is 6.283 or blah, blah, blah. It's actually 2 times pi. So you see that it has divided this interval 0 to 2 pi into 49 equal intervals, and there are 50 points if you include the endpoints. The endpoints are included by default here. And if you want to compute this, the sign of this particular array, all you have to do is to just call the sign function. Again, the sign function is defined both in the math module and in the NumPy module. Okay, so we are going to use the sign function in NumPy, and I'm going to act it on this array. And if I do that, it automatically and you print y, you see that it has computed the values of the sign of the corresponding entries of x. It's a very nice array-based computation. And once you have this, it's very simple to plot these two. We will use the plot function in pyplot. So you need to type pyplot dot plot x's comma ys. So if you do that, it should automatically give you this graph. Basically, this tells you, this shows you that if I plot x on the horizontal axis and y on the vertical axis, then it looks like this. Okay, I can also make it fancy by, it's a good idea in general to name your graphs. So let's name the x label as just x, and y label as y. And if you want to have grid, you would and if you want to have a label, let's say, then you can do a label equals sign, and then you can do something like pyplot.legend. Okay. So if you do a shift enter, then you see that it has this kind of a structure. Okay. And you can also play with the line styles. For instance, you can say line width equal to 2. And if you want it to be of, let's say, red color, then within brackets R, and then a hyphen to tell you it's a line, then you will see that it is a thick red line. If you also want to show the points, individual points, you just add an O here, and it will show you the curve with the points also. Okay, so all these kinds of fancy things can be done with pyplot. It's as I said, it's just a nice package to do all kinds of 2D graphs, and there's very good documentation. If you go to matplotlib.org, which is the web page which for pyplot, then you can go to examples, and pretty sure that, yeah, so once you go to examples, it's going to show you a whole lot of different things that you can do with pyplot. Okay, so it's quite good, and it gives you very high quality graphs, that publication ready graphs, if you will. You can create them with pyplot. So you can see a lot of examples. So if you want to understand how to work with any one of them, all you have to do is to click on that particular picture, and it will take you to the corresponding code that generates that particular image, and you can play around with it and learn more about it. So it's a very nice package. Good. Now, these are some very, very basics of how Python looks and feels. Okay, so it's a high-level programming language, and it's extremely elegant. Because once you start writing Python, what you would realize is that the code reads almost like how you would describe the program, okay, in plain English. So in that sense, it's a very nice software, and I encourage you to check it out. Okay, so let's now very quickly do some automatic differentiation with Pytorch, and then we'll take a break. Okay, so the first thing we want to do is to let's say that I have this functions. This function square, right? The square function takes a number and gives you the square of that number. Now you want, let's say you want to compute the derivative of that function. Now that's very simple. You know that the derivative of x squared is just 2x. Okay, so let me just write it down. Not because you don't know this, but because I can illustrate how to write math here. So the derivative of the function And if I write anything within dollars, you can use LaTeX symbol. F of x equals x squared is, and then if I want to write an equation, I can do it like this. You can again have any LaTeX command here. So I'm just going to do df dx is to x. Right. So this is something you already know, right? So the derivative of the function x squared is 2x, and so let's implement that. Okay. So def d square d square as the function, which sorry, should have just returned 2 star x. So what this tells you is very simply that I've now defined a function which I call d square, which is nothing but the derivative of the function square. So comments in Python are given by a hash. This is the derivative of the function sqr. Okay. Now, in the context of simple functions, you can do this. You can actually manually define the derivative, but it's often very cumbersome. So what we're going to do is a way to automate this without even actually writing the function. So as a backup example, let's compute the following. So if I take y is, so let me first define x as, let's say, 2.0 and y as sqr of x, and dy as d square of x. Okay, so y should have the value 2, and the derivative of y at the point x is nothing but 2 times 2, which is 4. So if I print x comma y comma dy, this should print 2 comma 4, right? And that isn't sorry, 4 comma 4, right? So square of 2 is 4, and 2 times 2 is also 4. So maybe not a great idea. So I'll make it 2.5. So it should be 2.5 squared and 2 times 2.5, which is 6.25 comma 5. Great. So we have a baseline here. Now let's try to see how we can do this derivative without actually writing this function. What if I have access to only the function sqr? Okay, we have written the function sqr earlier here, right? So it takes a little bit of time to go there. We have defined this function here. Is there a way to automatically differentiate this function? Okay, and we can do that using automatic differentiation, and I'll show you how to do that using Pytorch. Okay. The first thing you need to do is to define a variable as what is called as a tensor. Okay. Now Pytorch uses this fancy word called a tensor to describe a multidimensional array where you have this automatic differentiation features built in. Mathematically, a tensor is a much more beautiful object. It's very rich. It's a multilinear map and blah, blah, blah. This has nothing to do with that. This is just a very fancy term. You know, many of these machine learning people have a knack for giving very fancy terms to very dumb ideas or very simple ideas. You take an iterative algorithm and rebrand it as learning, take an optimization problem and call it as deep learning and other. It's not really something new, okay? But it is what it is. So let's try to define a tensor. I'm going to define a tensor as follows. You're going to use this torch.tensor function. Okay, this function, what it does is it takes an object and gives you back a tensor. So in this case, I want to take the object x, okay, and I want to have it of the type float. Okay, instead of a double, I want it to have a float for reasons that actually right now it's not required. I'll just have it as this particular form. But I need this additional argument, which is that I want to set requires grad equals true. Now, what this particular additional argument tells PyTorch is that you're going to track the derivatives with respect to this variable. Okay. Now, what this means in particular is that I'm going to evaluate a function of x, and I'm going to query the derivative of that function with respect to x. That's what I'm going to do. And so if I have, let's say, this basic structure, if I say print xt, if I type this, then you see that you get a tensor whose value is exactly the value of the function. So x has a value 2.5. So the tensor is also an object which has the value 2.5. So it's also a variable, except that it has inbuilt functionality to track derivatives. Okay, so don't be misled by this name. It's just a container which has more interesting features. Now, once you do this, okay, suppose I want to evaluate the function y like this. Let me do something. Yt is sqr of xt. Okay, this looks very similar to what I've written here. Instead of x, I have xt standing for x tensor. and instead of y I have yt. Okay, these are just names. So, and if I print yt, you would get exactly what you would expect, 6.25. Right, 6.25 is the square of x. So far xt behaves just like a normal variable. Now here's where things get interesting. Okay, suppose I want to take the derivative of this function square with respect to its argument at the point xt. All we have to do is to do this magic command yt dot backward. That's the whole magic command. Okay, so if you type yt dot backward and press enter, this harmless command automatically does this back propagation for you. So remember I showed you that graph here where you set up all the do the computation, set up the computational graph, populate the edges with the corresponding derivatives, initialize the seed, back propagate it all the way to get the derivatives. All this operation is done by this innocuous looking command yt.backward. And once you do this, the derivatives of this function yt, which is square of xt, with respect to xt, is stored in the grad attribute of this function, of this variable. So this extends that xt has an attribute called grad. Okay. Now, if you query this, you should get 5.0, which is the derivative of y with respect to x. So let's see if it happens. If you do that, you see that it gets the tensor 5. Okay. Now this is great because when you evaluated this function, you did not evaluate the derivative like what you did here. You did not write a new function called d square and then compute the derivative, but rather you just accessed the grad attribute of this xt tensor, which automatically got evaluated when you ran this magic command yt.backward. Okay. Now this is the nice thing about Pytorch, which is that you can have arbitrarily complex functions and yet it can give you it can give you the derivatives effortlessly. Okay. For instance, let me give you another example. Suppose I define the function g of x as, let's say, uh, x squared times sine x. But now, instead of using sine, I'm going to use torch.sine x. Okay? The reason is that torch re-implements many of your, PyTorch re-implements many of your mathematical functions, like sine, cos, exponentials, all the simple functions. The need for re-implementing them is that when you do this, it automatically understands the computational graph very well and how to store the derivatives, how to back propagate the derivatives, and so on. Okay. So if I want to have a function g of x like this, then of course I can evaluate g at the point xt. And now, if you look at, so you can just use it as a calculator also, 2.5 star 2.5 dot sine 2.5 is exactly 3.7405. You should get that. Okay, so you see that's the same number that you get here also. So, so far the function evaluation has just given you the value. But if you want to calculate the derivative of g with respect to x at the point xt, all you have to do is to run the magic command g.backward. There's one small catch though, which is that when you evaluate the gradient, by default, PyTorch accumulates the gradients on top of what you have. Now you don't want to accumulate because xt.grad already stores the function value, the value 5. So you first set it to none. Okay, so this is an important thing. So keep in mind that this is true. So you first set it to none. None is a Python keyword which is used as a catch-all for saying this is nothing. Okay, and once you do that, you can run your function g of xt backward. Okay, this magic command automatically computes whatever you want. And just to keep it simple, I'll rename this as a new variable z. Okay, and I'm going to do z dot backward. So it looks clean. So z dot backward, and that it has automatically computed the derivative of z with respect to x for us. Okay, and to access that, all you have to do is to just ask for xt.grad, press enter, and it will give you the derivative of this function g at the point xt, just 2.5. Now, is this correct or not? Okay, we can manually compute the derivative, right? So because you know that so let's do a check. The derivative of f g of x equals x squared sine x is, what's the derivative? So if I look at g prime of x, you know from basic calculus that this is 2x sine x plus x square cos x, right? So you know that this is true. This is the derivative. So let's compute this quantity at the point 2.5, right? So it's the 2 times 2.5 times sine 2.5 plus 2. X is 2.5, right? Yeah, plus 2.5 star 2.5 star uh, numpy cos 2.5. Okay. Now, if all goes well, it should be minus 2.014, and it's giving you some other value. Okay. So, can someone tell me if I made a mistake somewhere? What is the value of xt? 2 into 2.5 into sine 2.5 minus 17, and this is the nice thing about live coding, right? So it's oh, sorry. Yeah, that's absolutely right. Thank you so much. Uh, the comment is spot on. This should be 2.5 and not 2 star 5, right? Uh, thank you very much. Who pointed that out? Harish. Thank you very much, Harish. You saved me a lot of time. Yeah, it's 2.5 times 2.5. And yes, now we have the same answer. It's minus 2.0148 and minus 2.05. That's great. Yeah, so this is great because if you look at this situation, right, if you wanted to compute the derivative of this function, you needed to manually compute this big quantity and then evaluate it and get it. But you didn't have to do that with Pytorch. All you had to do was to define the function only and then run the backward function on that, call the backward function on the wanted variable. It automatically computes the derivatives. So if you look at Pytorch, the way it implements, it's basically doing this back propagation for you. It automatically does this for you and gives you the final output. Yeah, that's the power of Pytorch. Okay, so you don't have to manually sit down and write derivatives. Why is this interesting, right? Suppose that you have an optimization problem like this. Okay, so suppose that you have an optimization problem like this. I want to find the minimizer of an objective function f that takes n real variables and gives you one real variable, except that n here is, let's say, 1 million. This is not uncommon, okay? If you look at typical modern day neural networks, they'll have 1 million or more parameters, right? So if you want to sit down and write the derivatives of each one of these things, if you want to write the analytical form, it's going to be a nightmare. But if you use the automatic differentiation of Pytorch, it's one simple command. Run the backward function. It'll back propagate the hell out of your function and get you the derivatives. Okay, so that's great because it really simplifies the job for you. Okay? And you can begin to focus on the larger level picture. Now that's it. I encourage you to look into the details of how automatic differentiation is implemented. I gave you a simple start using some basic functions, but I encourage you to read more and get more details about this. Okay, good. Now I think this is a good time to stop. We can take a small break now, and once we are after the break, we can continue the discussion. So it's 3:58 right now. I propose that we meet at 4:05, so that gives you a 7-minute break. So if you have any questions, I'll be happy to take them, or if you want to just chat, or if you want to tell me a story, I'm happy to hear. So, okay. Just going to take some water. My throat gets especially parched when I give long lectures. So. Uh, can I have some feedback on whether people were able to follow along while we wait for a file? Someone has their mic on. You're almost there. Just open your mouth and talk. Yeah.
I think it's me. I'm just waiting.
You misled me. Yeah. I was very excited that someone is going to talk.
I was just waiting for to prod someone. I guess. Let me see.
Oh, no, I don't like prodding.
Okay, okay, okay.
Let people talk if they're interested.
Okay, okay,
If they're not interested, it's okay.
okay.
Yeah. You see, Ankit has left the meeting. That's what happens. What he doesn't realize is that I don't like to single out people and ask questions. Anyway, so I think there is a comment here. Oh, you're writing the code along. Okay, that's good. Were you able to follow the code, and were you able to get the same results? Oh, yeah, that's great to hear. Yeah, Python is a beautiful language. Okay, and it's you can use that for very simple research. Programming. You can use it for really complex programming. Like Pytorch is an entire package for machine learning written in Python. I mean, not entirely in Python, but there are tons of nice packages which are written entirely in Python. It's used in all kinds of research activities. And the Fossee team, actually, you had a mention of Fossee in the morning. So let me just mention this. If you go to fossee.in, okay, let me get the link. And if you go to Python here, you can see this link for a Python self-learning course. So I'll just give you the link here in the. So these are lectures by my amazing colleague, Professor Prabhu Ramachandran. So I collaborate with Prabhu also, and he's a resident Python expert at IIT Bombay. And if you have ever heard about the 3D visualization tool Mayavi, Mayavi is basically Prabhu's creation. It's used all over the world now. So if you type for Mayavi, this is a 3D scientific visualization package, which was created by Prabhu, entirely in Python. And so we're talking about a real serious Python programmer here. So Professor Prabhu has created these wonderful lectures. Okay, it's a Python self-learning course. You can either get a certification for it if you wish, or you could also listen to it for free without getting a certification. But if I think the certified course is paid, I'm not sure. But this has wonderful lectures. Okay, if you want to understand Python, especially in the context of scientific computing, and you want to get started, I cannot think of a better person than Prabhu to teach you Python. And this particular, let me give you the link. Did I paste the link already? Oh, I did. Okay. Yeah, this is a great resource if you want to learn Python, and I encourage you to look into that. Okay, so it's a fantastic website. And Fossee in general is an entirely Indian venture, right, to create this open source software. We saw an example of that earlier today with the optimization toolkit, which Professor, what was his name? Okay, the earlier speaker, Mahajan, Professor Mahajan, yes, Professor Mahajan spoke about. So, yeah. Yes, it's built on top of VTK. And so Prabhu works in fluid dynamics. And he wrote this as a PhD, as a fun thing during his PhD thesis. When he was writing his PhD thesis, he just thought he'd take a month off and write this, and he basically created that during his PhD. So it's a fun. Yeah, yeah. Well, I will leave it to you to discuss that with Prabhu. He has a lot of very clear reasons why he doesn't prefer ParaView. Uh, and so there are lots of nice examples you can see of what you can do and with Mayavi. So, and it comes with the source code too, so you can check it out. And of course, this Python course is created by him. There are tons of resources for Python. Python is one of these very easy languages to learn. And, by no means is it the only language, though. If another very good language for scientific computing is Julia, and Julia has a lot of advantages compared to Python, and also some disadvantages. But end of the day, it's about what you're comfortable with. And I think if you're looking for good languages for scientific computing, Python, Julia, these are all great options. Yeah. Okay, it's 4:05. So should we start again? Akshay, should I start?
Sir, what about R package for scientific visualization?
Oh, R is a package specifically meant for statistics. Okay. I've not used R extensively, so I cannot comment about that. But I know colleagues who have used R for visualization in the context of probability, data analysis. So I think it has a lot of functionality for data visualization there. Yeah, but I haven't used it. Python provides a lot of nice functionality, so I rarely step out of Python for plotting needs.
Okay, sir. Okay, thank you.
Oh, I mean, there is no hierarchy here. I mean, I'm happy to. As I said, I'm very informal, so if everyone's okay to start, and we can start again. Okay, so let me share my screen again, slides. Okay, so we left off here. So now we have some idea about what automatic differentiation is and how we can actually use that to compute derivatives of functions without having to actually bother to sit down and write the function and code the details. Now what I'll do is I'll get into the actual subject, which is physics-based learning, right? What is it that defines physics-based learning? So we will look at that with a bunch of examples. And before I do that, I want to okay, very quickly talk about neural networks, okay? Because what I want to do is to contrast physics-based learning with a standard database learning, okay, which is what you call as machine learning, etc. So there is a difference between physics-based learning and standard machine learning, and even though they have a lot of similarities too, okay, it's important to appreciate that before we move along. Now, in standard regression problems in machine learning, the idea is that if you're given a data set, okay, suppose you're given a data set consisting of n data points, where you have the features which are x, which live in a space Rd, and the output is y, which lives in R, it's just a real number, and you want to find a pattern in this data. So what you want to understand is if this data is representative of some underlying function, or if it is drawn from an underlying distribution. You want to find out what that is. So it's a very simple inverse problem. And that inverse problem is what is called a supervised learning. Okay, the goal of supervised learning is to basically find a function from a specified function class that best explains this data. Okay, now the moment you hear words like that best explains or etc., these kind of superlative usages, you immediately have an alarm bell ringing at the back of your head saying that, okay, yeah, maybe there's an optimization problem involved. Okay, so what you can think about is if you think about this function space as a collection of points in an abstract setting, you want to find the point in that abstract space where a particular function is minimized. A particular function. What is that minimum? What is the function that you want to minimize? It's the discrepancy between what your function would predict and what the data what the data says happens at that particular point. Okay, so when you look at this discrepancy, if this discrepancy is minimized, then that would give you the best candidate for potentially explaining the data using that function. Okay? So mathematically, the way you would do it is if you look at the data, ith data point and the value is yi, the prediction based on my function f is f of xi. The discrepancy between the two is what I specify by a loss function L. Typically, this L is just a simple Euclidean distance, squared distance. So in this case, it's just in R. So you can think of it as the difference of y minus z whole squared. Okay? That's a simple enough loss function. It's the standard L2 distance in R. Now, of course, you have n data points, so you will have the sum of all these discrepancies, and that gives you the total loss function. Okay. Now, what you want to do is you want to search among all the functions belonging to a particular function space, and you want to minimize this particular loss function. So as you can see here, this is exactly what we have been studying so far. This is a standard example of a constraint optimization problem. What is the objective function, which is it's just the sum of I going from 1 to n, L of yi f of xi. And the constraint is that the function that you're fitting is taken from from a specified function space f. Now, depending on what this function space is, you get different kinds of minimization problems. Okay, if f is the set of all affine functions, you get the standard linear regression problem. If f is the set of all neural networks, you have a deep learning algorithm, whatnot. Right, so it's just depending on how you choose f, you get different supervised learning algorithms. Now, again, the way we would solve this is by using a gradient descent algorithm. There's one catch, though. Typically, function spaces are infinite dimensional. Okay, so you cannot apply any of the standard techniques that we have been studying so far. All our examples have been finite dimensional optimization, right? So if you look at, for instance, the starting point, it's Rn. In other words, n is a finite number. Any point in Rn is a collection of n numbers. It's not a function, it's just a collection of n numbers. So you're dealing with finite dimensional optimization. Whereas if you have a statement like this, you want to minimize f belonging to a function space, this becomes an infinite dimensional optimization problem, which in general is much harder than finite dimensional optimization. Okay, so in practice, right, people don't solve the infinite dimensional problem, but rather this function space is going to be parameterized by a set of finite parameters. And you do optimization with respect to those finite parameters. So what you're actually doing is a finite dimensional optimization problem. Okay, so for instance, if you take linear regression, this function space, let's say in one dimension, f would consist of all functions of the form ax plus b, right? Y equals ax plus b. Now, for every choice of a and b, you get a different function. So even though it's an infinite dimensional space, it's actually finite dimension. Even though it's a function space, in this case, it's actually a finite dimensional function space because it just depends on a and b. If I specify a and b, I can get all the information that I want, right? So that's the idea. So you want to reduce the infinite dimensional problem to a finite dimensional one by choosing this function space to be a parameterized function space. Okay, and that's the idea. In a special kind of these kind of parameterized functions is what are called as deep neural networks. Okay, now this is just a composition of elementary functions that has very interesting properties, and that's the reason why it is so popular. Okay, it has its own disadvantages too, but because it is very popular, I'll just give you the broad idea behind this, and I'm sure many of you know this already because of the popularity of these kind of algorithms. The idea is that you transform an input to a specified output. So suppose I want to represent a function which takes two real variables and gives you one real variable. The way you do that is by transforming this particular input into a bunch of intermediate values using simple compositions of linear and nonlinear functions. Okay, so here you see that this input, the two-dimensional input, is first converted to a three-dimensional hidden layer. So these two numbers are transformed to three numbers, and they are in turn transformed to another set of three numbers, and finally recombined to give one number. Okay, and this specific detail in which these functions, this input is transformed to the output, that's encoded in what are called as the hidden layers. But if you zoom in into any one of these particular links, okay, how these are constructed, what you would see is that it is at its root a composition of a nonlinear function called as an activation function and an affine function, which is just a simple something like a linear function. It's not a, it's affine technically because of this non-zero value of b. Now, a deep neural network is just a composition of these affine and nonlinear functions back to back. You first apply an affine transform, then apply an element-wise a nonlinear function, then apply the affine transform, then the nonlinear function, etc. So this composition of elementary linear and nonlinear operations is what characterizes a dense neural network. Okay, and as you can see here, once I tell you what the parameters involved in these individual linear functions are, okay, sorry, affine functions. Each affine function is of this form. It's going to be some matrix multiplied by its input plus a constant vector. Then if I know the matrix W and the vector B, then I know exactly how T works. And sigma is just a known function. Okay, you can think of it as a sigmoid function or as a ReLU function. You can have multiple choices. But there is no parameter involved in sigma. It's just a function that is given to us. Now, so all the parameters are contained in W and B. Now, each W is itself a matrix and B is a vector. So in other words, the combination of W and B is a finite dimensional quantity. Okay, so I should have written this as WL and BL, but it's okay. I'll correct it later. So you see that in this case, the parameters of this deep neural network are just these collections of numbers, W1, B1, collections of vectors and matrices, W1, B1, W2, B2, etc. And the number of such should again be capital L. And the number of such representation layers that you have, okay, defines the depth of your neural network, while the number of neurons you have in each layer tells you something about the width of the neural network. So you can construct a lot of different neural networks depending on how you choose the internal topology or the internal connections of your network, and depending on that, you'll get different function spaces. But for our purposes, right, all you really need to know is that the set of all neural networks with a specified architecture is just a function space, which we will denote as dnn of x comma theta, which tells you that if I know the parameters theta, which means I know the weights and the biases W and B, then in principle I know this function. This is just a very fancy function. Instead of talking about the set of all affine functions, I'm talking about the set of all functions that can be written as a composition of these affine and nonlinear functions. That's it. Okay, it's as simple as that. And once you understand that this is just a parameterized function space, your optimization problem just simply becomes minimizing this loss function with respect to functions drawn from that function space. This function space just becomes the set of all parameterized, set of all neural networks with a specified architecture. That's it. You can apply all the algorithms that we have studied before, gradient descent algorithms, etc., and find the optimizer, find the minimizer. Okay. So the reason why I think these neural networks work is a subject of intense research, but empirically they tend to have a lot more success in studying high dimensional functions in comparison to what traditionally is used in optimization, like simple polynomial bases or something like that. That's the reason why people are sometimes excited about it, but don't be carried away. It's not some magic, or it's not something fancy. It's just a very fancy way of talking about a very simple idea, which is finite dimensional optimization, which is what we have been studying in this workshop. So I won't be making a big deal about these neural networks because it's part and parcel of the optimization. It's a small part of optimization theory. It's not a great thing by itself. Okay. Now, once you have, if you want to use a gradient descent algorithm to compute the minimizers of a given neural network optimization problem, then in principle you update the parameters like this. This is a standard gradient descent update, right? So you move in a direction away from the direction of the gradient. Okay. Yeah, that's menacingly close. Okay, fine. It's gone to a different place. Okay, yeah. So you move away from the direction of the gradient. Okay. So the gradient of the objective function with respect to the parameters theta is what is given here, and you want to move in a direction opposite to that. So empirically, right? What we have seen also earlier that it's easy for a gradient descent algorithm to get caught in a local minimum, and we have seen many examples of this as part of this workshop. Now, in how do you avoid getting into a non-optimal minima? Right? So it's a local minima, but not a global minima. But it's not the best place to be. Now, in practice, what people use is what is called as stochastic gradient descent, and the idea is that you don't take the step at once, but you compute each of these gradients individually, right? So if this is the sum of n terms, this particular objective function has an additive structure. It's not specified as a capital L of theta as some function, but it's provided as a sum of n individual functions of theta, right? So what you do in a stochastic gradient descent is to compute the derivatives with respect to each of these individual data points, and then successively update it. Okay, and this entire cycle is called as one epoch. And so one epoch is exactly what you call as one iteration in a gradient descent algorithm. In a standard gradient descent algorithm, from step n to step n plus 1, you just have one computation. But in a stochastic gradient descent algorithm, that itself is broken down into many steps. Okay. Now, in practice, of course, this can sometimes be very costly if you have a lot of a lot of data points. So you can club together, instead of evaluating the derivatives with respect to all the data points, you can use a subset, which is defined by what is called as a batch size. And in this case, it's called as a mini batch stochastic gradient descent. Okay? And that's the preferred approach in practice. And of course, there's a whole zoo of algorithms. Okay, we can have accelerations for this using momentum. You have all kinds of algorithms like Atomax, RProp, whatnot. I mean, you have like a zillion algorithms which you can use to find the minimizer. But ultimately, you need to understand that it is nothing more fancy than this very simple step, right? So if you go back to our beginning, I told you that an iterative algorithm is construct a sequence. So you want to construct a sequence that goes towards a local minimizer. That's it. And how you construct this local minimizer is where, how this construct the sequence is where all the drama is. In a gradient descent algorithm, you construct it like this. In a stochastic gradient descent algorithm, you have a slightly different means to construct the sequence. And whether you're using Adam or Atomax or any of the zoo of algorithms, you would come up with a different sequence. And depending on the problem at hand, different optimization algorithms might have a better way to navigate the loss landscape, and some might perform better than the other. Okay, so it's largely an empirical art, unfortunately, at this point in time. But it's enough if you just understand stochastic gradient descent, or the idea behind stochastic gradient descent at this point in time. Okay, good. Now, with that said, I'm going to show you a small demo of how supervised learning works and how that contrasts with physics-based learning. Okay, I'm going to use a very simple example and show you how these two are related. That's the best way to get a sense of these two. Okay? Now, in the interest of time, what I'm going to do is I'm going to use code that I have already written. Okay, so you can find the code again for those of you who joined late. You can go to this particular link. I've given the link here. You scroll up the chat window. You should see this link, GitHub link, github.com, and this is my page on GitHub. And you will see this particular repo, which is AICTE Workshop 2021. If you click on that link, you should be able to. It should take you to this particular page. And if you open this, if you press this IPyNB file, basic physics-based learning IPyNB file, that contains all the code that I'll be discussing. So initially, our first hands-on session involved automatic differentiation. So you can see some examples here. And now I'm going to run this example, which is inspired by this online textbook. Okay, there's a very nice book called Physics-Based Learning, Deep Learning. So I encourage you to check out that book if you are interested. But what I'm going to do is the following, right? So we are going to generate data that looks like a points on a circle. It is exactly generated like that. And then what we're going to do is we're going to learn what this function is using both supervised learning and physics-based learning. And immediately you will see why they are both different. Okay, so instead of writing the code and then telling you each and every line, I'm going to run you through the code. I'll copy paste the code and then show you the large idea behind the code. The reason is simply that one, we don't have enough time, and two, most of you don't have a knowledge of Python, right? So understanding all these details would be a little too much at this point. So let's just try to get the broad idea right now. Okay, so I'm just going to copy this code. Okay, and so I'm going to paste it here. So what you see here is that I'm going to generate, I'm writing a function here to generate data on a circle. And the idea is quite simple. First, I generate points between equally spaced points between -1 and 1, and then create the function y equals square root of 1 minus x squared. That gives you the unit circle. And depending on, I randomly flip a coin, and half the time I take a point in the upper branch of the circle, and half the time I take a point in the lower branch of the circle. Okay, so if I let's say I want 200 points generated like this, I can I just call this function with the argument 200, and then I can plot what those points look like, and you will see something like this. Okay, and notice that every time you run this program, you will get a different result. Because, for instance, the last time I ran this program, which was in the GitHub repository, what you see here, that looks very different from what you see here. Okay, the reason is that you're using a random number as part of the code. So whenever you have a code that it uses random numbers in an essential way, then the output of that code will be different every single time you run it. So especially these are stochastic programs, if you will. And when you're dealing with code that uses random numbers in an essential way, you have to make sure that your results are consistent with that randomness. Okay, it should not be the case that you get entirely different results every time. There should be a pattern to the madness. So in other words, you need to be aware of what probability distribution of the outputs you should expect, and whether your code is actually able to produce that probability distribution. Okay, but that's a different discussion. For now, you just need to notice that the output that you get here, the output that you would get when you run this in your browser, if you're doing it, okay, all you have to do is Control-C from here, and then Control-V here, and press Shift-Enter, and you should get a result, but you would get something different. Okay, you will not get exactly the same as this. You will get points on the circle, all right, but different set of points. Okay, now what we're going to do is to, this is the data point. So if you go back to our slides, you see that our goal was, if I give you a bunch of data points here like this, right? This is my set D. So the set D that you're talking about is just this set D. This is set D, and I want to find a function that fits this particular data points, this set of data points. In other words, I want to find a function from a pre-specified function class. So can someone tell me, okay, you can think of it as a mini quiz here. Is it possible to fit any function to this data at all? I'm just curious. I want to ask as a general question. Can someone tell me, is it possible to fit a function to that data? To this, oh, sorry, I'm already there. To this data. So the question I'm asking is, okay, who said that? Oh, actually, okay, actually, yeah, great, yeah. Thanks, Akshay, for the feedback. And I want to hear from the participants also. Anyone, if you're not comfortable, it's okay. I'm just going to wait for 2 seconds and then move on. But if you want to talk, yeah. Oh, sorry, I didn't even see it. I was far up. Okay. Yeah, that's actually right. You cannot fit a function because a function by definition has the signature. A function can have only one value. Function from, let's say, f from R to R. A function can have only one value for a specified input. Okay, so this is by definition, right? So if I have a function of this signature which takes a function, which takes a real number and gives you back a real number, by definition, if I give a particular input, it cannot have two values, it can have only one value. But notice what is happening here. If I take an arbitrary point here, okay, maybe I can add a grid here. So let me do that. So and then plot don't worry about what I'm doing here. I'm just doing some nonsense. Y is, oh, sorry, x should be 0.5 minus okay. So what I'm doing here is just drawing a vertical line, simply. So if I look at this particular point, which is the point 0.5, x value is 0.5. So let me just plot that point. Okay, so if I look at the value at this point, x is this point given by the red dot here. Now, if you draw a vertical line at this point, you can see that it intersects this particular data set at 2 points, right? It intersects this, suppose this data set is generated by a circle, which is the ground truth, and it intersects the circle at 2 points. In other words, for this value of x, there are two values of the function, two values of this particular data set, which means that it cannot be represented by a function. By definition, a function can take a value and give you one value only. Okay? This is a mathematical definition of a function. You can have multiple values giving rise to the same y value. Indeed, if I take a point -5, that will have the same y value if I focus on the upward arc alone. But that's not what I'm saying. I'm saying that for a given x value, it cannot have two y values. Right? So this is a problem. So this is the reason why supervised learning, any kind of supervised learning, would fail for this particular example. Okay, and this is something we know beforehand. So let's anyway try to fit in a complicated nonlinear function and see what happens. Okay, so let's bring in the newest candidate, which is everyone is excited about, which is basically a neural network. In Pytorch, you can create neural networks quite easily. Okay? So it's as simple as creating a class. Okay? A class is a way to organize data and functions that operate on that data alone in one single unit. Okay? You can think of it as a conceptual generalization of a function, but it is much more. Okay? I'm just trying to tell you without getting into many details what a class is. And what you can do is you can define a neural network very simply by telling what are the hidden layers and how many neurons are present in each hidden layer. Okay? So in this case, I'm saying that factoring out all this fancy, what do you say, notation and a fancy syntax here. What you have here is basically saying that I have a linear layer which takes one input and gives you n hidden outputs. So this takes a neural network where the first input layer is just one neuron. The first hidden layer has n hidden neurons. The second hidden layer takes n hidden neurons to n hidden neurons. And the final layer takes n hidden neurons to one neuron. So what is written in these 3 lines of code is exactly what you're seeing in this graph. So if you look at this figure, it takes 2 to 3 to 3 to 1, right? Now, instead of 2, you have 1 here. So the way you want to think about it is the first layer contains is 1 comma 3, second layer is 3 comma 3, and the third layer is 3 comma 1. Okay, so if you replace 3 with n hidden, that's exactly what you get here. So it allows you to define these hidden layers, and you can do this for arbitrary complexity. If I want to have a neural networks with 3 hidden layers, let's say, I can add a third layer here, which is torch.nn.linear n hidden to n hidden. Of course, the number of neurons can also vary. You can define it like this. And how do you evaluate the neural network? You define a function called forward, which which basically does the function evaluation for you. So if you remember your, let me go back to the slide, sorry about this. So if you remember your neural network, you see that it is actually a simple composition of linear and nonlinear functions. You first act a linear function, and then you have a nonlinear function, and then a linear function, and so on. That's exactly what you are doing here. You take your input x, you perform an affine operation, which is what layer 1 does, and then you act a nonlinear function. In this case, I've just used tan x, tan h of x, and then you have the second layer, which is basically a linear layer, which tells you that I have an affine function that takes n hidden inputs and gives you n hidden outputs. And then you use a tan h nonlinear activation function after that. And then the third affine layer, and now we have already introduced one, so I'll introduce another activation function, tan h x, and then of course your final output. Notice that I'm using the same variable x to denote each of the outputs again, and this is something which is again nice about Python and Pytorch design. You don't need to create new names to create the intermediate variables. It automatically keeps track of the fact that the variables have been reassigned, so you don't have to worry about that. And once you do this, that's it. This is all the code that you need to create a neural network. So if I create a neural network, let's do that. Let me just copy this. Okay, so if I copy this piece of code and paste it here, that's it. You have created your neural network, and this is what this tells you is that if you create an instance of this particular class, that will represent a function that looks like this. Okay, in other words, a function that looks like that. Remember that ultimately a neural network is a function. That's it, nothing more than that. Right? It's a parameterized function. So as long as you are able to tell how to set up that function, you are good. And because it's a finitely parameterized function, you just need a finite number of parameters. And that is what we're doing here. What we're saying is that the parameters are defined by the topology. Sorry, the topology defines the neural network architecture. And then the parameters are initialized randomly. The nice thing about Pytorch is that all that is done automatically for you. You don't need to sit down and write down, here is the matrix, here is the bias, here is the actual multiplication, here is the element-wise operation. You don't have to do any of those lower level details. It automatically takes care of that for you. Okay, and that's great, because once I have this, then all I have to do to create my neural network, suppose I want to create a neural network, is by simply calling this particular class. The name of the class is CircleNet. Okay, it's just a very fancy name. Okay, one thing you will realize when you do machine learning is that people give very fancy names for very simple ideas. Okay, and unfortunately the larger public think that there is some magic involved and there's something fancy going on. Okay, it's just PR nonsense, because these are pushed by big companies and they have to generate revenue, and how better to generate revenue than take a simple idea and give it a very fancy name and make money out of it, right? And in the grand tradition of that, we will take a very simple function and give it a very fancy name, CircleNet. Okay, why not? You can create whatever in fact, if you want to give an Indian name, you can call it Shunya. That's true on multiple levels, and you can create whatever you want. Okay, so let's go with CircleNet. And of course, to define the architecture, now I just need to tell you the number of the number of neurons in each hidden layer. So let me first define that. So let's say that I want 10 neurons. Okay, so let's say I have n hidden is 10. I have 10 hidden layers in 10 neurons in each hidden layer. So I'll just pass on that value, and hidden is the variable, so that equals this variable in hidden, and that's it. We have our neural network. Okay. Now, what does a neural network do? It basically is a function which takes an input and gives you an output. So let's give it an input and see what output we get. Okay. Now, the way you want to give an input to a neural network in Pytorch is that it should be a tensor. It should be a tensor array. So if even if you're, in this case, our neural network takes one input and gives you one output, but your input cannot just be a number. Okay, so if you do something like x xx is or the, x1 is say 0.5, and let's say I do dnnsl of x, you will get an error. Okay, even though it's a function which takes one input and gives you one output, you would incur an error if you do this, because this is in the wrong format. X is just a number, whereas it requires a tensor. So what you need to do is to convert this number into a tensor. Okay, and you will see that even this throws an error. So if I do this, you will still get an error. Okay, so now you might be wondering what is the reason why this is throwing an error. Now the reason is that this is a tensor, it's a scalar quantity which is of the type tensor. What you really want to pass on is an array consisting of just that one number. Okay, the reason is that if you do something like this, then okay, d type. Yeah, so this is again all kinds of things can go wrong when, oh sorry, x1. I've been doing this wrong all along. It's not x, it's x1. So these kinds of errors would happen all the time. Actually, make sure that every single thing I said earlier is wrong. Okay? For instance, if instead of x1 I just do 0.5, you should get an error. Okay, if I do something like torch dot tensor, even if it's of type tensor, you will get an error because it requires an array. What actually works is if you send in a singleton array which consists of 0.5. If you do that, then you see that the output is again a tensor, which is of this particular form. Okay. Now, the reason why Pytorch has this specific feature is that in general, it's meant to operate on functions which are higher dimensional, right? So a higher dimensional input is defined as a vector. So if it's a function which takes, let's say, 3 real variables and gives you 1 real variable, then your input would be a vector of size 3. So 0.5, 0.1, 1, etc. So now, you see here, right here, is all that you need to know about a neural network, right? So because it's a function, so you have created a function, you know how to evaluate the function at a particular point x. Now this is a randomly initialized neural network, which is why you get this random value. Okay, now you can actually plot and see what those values are. Okay, for instance, if you remember, our x's was just that array of -1 to 1. You can see what the value of of the neural network is. Okay, so for instance, I can do something like uh, don't worry about the syntax, it's slightly complex. You can do something like dnn you have to process this input x into a form that Pytorch likes. Okay, so you first need to do torch.tensor xs, and you have to change the type to float, 32, and then okay, and then you have to do this thing called unsqueeze. Okay, I don't want to get into the details of why, but that's just to make sure that it has the right data structure. Okay, so unsqueeze 1. So if I do something like this, it will compute the values of y that is generated by this neural network, and then you can plot x and y. So you can do pyplot dot plot x's comma y's dot squeeze. So if you do that, it will okay. Maybe I'm making a mistake here. Okay. sorry about these fancy syntax, but I didn't want to get into the details here. But the larger point I wanted to tell you was you created a random neural network. The random neural network has, uh, it's some function. Okay, so if you just copy this piece of code and run it in your machine, you will get a different curve. Okay, and what's your original data? Your original data was this, right? It's a set of points. So let me just plot that. So let me copy that and paste it right here. And by the way, these are not there in the GitHub notebook, so don't worry about that. Okay, sorry. This is, I'm creating the same name, so that's creating the problem. Okay, so let me rerun this. Sorry about this. I created the same name Wise by mistake. So I'm creating a different name now. So Wise is 0. This should work. So if I run this. Yeah. Okay. So you see that this is the state of affairs right now. So this is my data points, which is the set of points that you see as the blue circle here. And what I've drawn by this, let me change the color. So it's visible. So if you look at the randomly initialized neural network, that is actually representing this curve, this red curve. Okay, so obviously this is a randomly initialized neural network, so obviously it's not going to represent the data properly. Now the goal in supervised learning is to basically change this neural network to make it look more like the data. Right? So if I give you just the data in the top, then you can train the neural network to fit that data. But because you don't have any function that will fit this data well, you will see that this neural network cannot perform any better. Even after you train, it's going to look something like this. Okay, and that is what the remaining part of the code does. So what you're seeing here after this, right, is how you do this gradient descent algorithm with Pytorch. And because of the fact that you are using a stochastic gradient descent, you need to be able to pick up subsets of the data to evaluate the loss functions and stages. Okay, and the way you would do that in Pytorch is by using this data set and data loader classes, which are given to you. Again, I won't go into the details of all that, so I'll just provide the code so that you can read up about these and then play around with it. Okay. Of course, I cannot get into all the details in the interest of time, but it's not difficult. Okay? So it's just, so let me copy this piece of data, this piece of code, just to illustrate how it all works together. Dot data set. Okay, I'm just importing those necessary classes from Torch, and then I'm pasting this. Okay, so what I've done here in a larger sense is that I have, from the data set that I have, which is basically the set of x's and y's, which is this blue dots here, I'm creating an object of the type data set and calling that with a data loader. These are options in Pytorch, built in Pytorch, which basically do the equivalent of sampling. Okay, so suppose I have a large data set. When I want to run a stochastic gradient descent, I want to just focus on a small batch of the data. How small is that batch? That is decided by the batch size, which in my case is 25. And I'm going to call that this particular function, what it's going to do, this particular code, what it's going to do is, it's going to look at the data that you have, okay, and pick out an arbitrary subset of 25 data points and give it to the neural network so that the neural network can learn based on that. So how does the learning itself happen? Okay, so if you go to the learning itself happens like this. Okay, so let me first copy this piece of code and then show it to you and explain how it works. And I'm again very sorry for being a little fast here. My goal was to give you an overview of how these things work. Oftentimes, getting the details right will take a little bit of time, okay? And you need a little bit of practice and encoding to get the details right, but that's okay. It's just I'm sure all of you would be able to do it if you spend enough time. Now, the way a neural network learns is encoded in this particular function train. So what you're doing here is to say that you first predict what the neural network would do. So this model of the inputs, it's going to what it's doing is the equivalent of, if you go back to the slides, it's doing this particular quantity f of xi. Remember, our loss function is basically the discrepancy between the data set, the actual data value, and the data predicted by our function. So what you want to do is you want to create to compute the function value predicted by the neural network, compare it with the function value that is, the data value that is provided to you, and this discrepancy is a loss function. But where things get nice is that when you want to minimize this, solve this optimization problem with a gradient descent, you need to compute its derivative, right? Manually calculating this derivative is a very painful task because you need to first take the sum of n derivatives, and each of these you have to then differentiate with respect to the parameters. So it's a derivative of the loss multiplied by the derivative of the function with respect to the parameters, etc., etc. So it's a pretty fancy, it's a very long computation, not difficult, but long. But the whole magic of Pytorch, if you remember our earlier discussion, is that we just had to run one command. If you run the backward command, it automatically computes all the gradients for you, right? That's exactly what will happen here. So you see that in the midst of all this madness, you have the single line, lost or backward, which is basically computing the gradients for you, okay? And that is where the whole magic of Pytorch is, okay? So if you were to write this by hand, okay, if you were to write this neural network by hand, and you were to manually compute the gradients and then solve it, every time you change the neural network architecture, so say tomorrow you're bored and you say, okay, you know what, I don't want a neural network with 3 hidden layers, I want it with 5 hidden layers or something like that, then you will have to recalculate it by hand, the various derivatives. But in Pytorch, the magic is that you use automatic differentiation, and therefore all you need to do is this one single command, okay, lost or backward. That's the magic. And it automatically computes all the necessary gradients for you, okay? Now, what you need to keep in mind is that there are these additional important things like zero grad, etc., which you need to, this is the equivalent of setting the gradient to none. Remember when we did the initial demo in automatic differentiation, where was that? For some reason scrolling is very slow. We set the grad variable explicitly to none, if you remember. Sorry, it's very slow, I don't know why. Yeah, so you see this line, right? So you had to explicitly set the grad variable to none before you did another calculation. And the reason is simply that if you didn't do this, then the gradients would be accumulated, which is not what you want. Okay, that the equivalent of doing that, instead of doing it individually for each of the parameters, which typically a neural network will have a very large number of parameters. And even the simple neural network that we have has lots and lots of parameters. Right? So it's a very painful process to manually set the gradients to none. And Pytorch again has this nice functionality wherein you can do it in one step like this. Okay, and once you have that, the actual act of computing itself, okay, now you have what you've done is you've computed the loss function, you've computed the derivative of the loss function. What you're left to do is to implement the actual algorithm, which is taking this step, right? So loss dot backward helped you compute compute the gradient of the loss function, and the stochastic gradient algorithm itself is about implementing this step, okay? And that is exactly what is done with this optimizer.step. So if you look at this line in the code, optimizer.step, it basically performs the optimization for you, okay? And the nice thing about Pytorch again is that you can replace this optimizer with any fancy optimizer. You can have a simple stochastic gradient descent, or a Adam or Adamax or whatever you want. Okay, you can use the appropriate optimizer, and that's it. So you see that the whole of the gradient descent algorithm that we've been studying is written in these few lines of code. Of course, this is specialized for neural networks, but you see that there's nothing fancy about it. It's exactly what we have been doing earlier. Okay. And the rest of it is the same. You just to say the number of times you want to do the iterations. You set up the learning rate, which is nothing but the step size. You initialize the optimizer. In this case, I'm initializing it to a stochastic gradient descent optimizer. Pytorch has a lot of common optimizers inbuilt in this torch.optim module, so you can always find it. Again, the loss functions that you want, the small l, right? So in this case, our discrepancy was a squared loss. If you go back to our this thing, our discrepancy was the squared loss, right? So this one is called as the MSE loss in Python, in Torch. And once you have this loss function, it's a simple matter of just calling this train function to implement your gradient descent algorithm. That's it. That's exactly what you're doing here. So you compute the loss. And then what I've done here in this piece of code is to follow is to write out in code what we saw in the slides. Okay? This piece of code exactly parallels what we have been doing in the context of Pytorch, in the context of the slides. And when you do that, when you press Shift Enter, it's going to tell you how exactly the loss varies. And I've also given you how to plot the loss. Okay, so in this case, saying that the loss is decreasing, but you see that the loss is still very high. It's still 0.6. Okay, which means that it is not really learning anything. So even though it is the loss is decreasing, it's not learning anything significant. Initially, our neural network, which was completely initialized at random, predicted something like this. Okay, predicted something like this. And now let's see what happens after it learns something, after deep learning. What you have done now is deep learning. Let's see how good this deep learning is. For that, you just have to copy this piece of code. This is testing. Okay, so I'm going to test it on arbitrary points, and I'm going to see how it fares. This is very similar to what we did earlier. Now we are going to look at the trained neural network, which has deeply learned something, and see. Let's see how good it is. Okay. So I'm testing it at 50 data points, and then I'm just computing this curve, and let's see what it looks like. This is the trained neural network. It's not any better than the initial random guess. So you had an initial random guess, and you had a very fancy neural network with stochastic gradient descent, blah, blah, blah. You did deep learning, and of course, it turns out that the result is quite bonkers. For the simple reason that the data set is of the form where no function can get it right. So it doesn't matter how complicated a function class you throw at it, it's always going to miss it. Okay, and this is something you should always keep in mind. Deep learning is not a magic solution. In this case, you see that deep learning didn't learn anything deep at all. It just gave you the illusion of learning something deep, but it just gives you a wrong answer. Okay? My point here is rather to tell you that it's easy to throw in fancy names like deep learning or neural networks, dense layers, blah, blah, blah. But ultimately, end of the day, it's an optimization algorithm. And if you don't understand your data very well, and if you don't know the problem, then you might end up with fancy results. Okay, and just to show that this is actually a problem with our with the way we have implemented it, with the way the problem is done with the way we have implemented it. Let's look at a case where deep learning is expected to work. Okay? For instance, I can comment out. I go back here. Let me. Sorry, the scrolling up is actually quite painful in this one. So if you look at this line, right? So this is the part where I randomly selected between the two branches. So if I comment out those two lines and then create the new data set. Okay, now my data looks like this. This can be fitted by a curve. So our neural network better be able to do it. So let's see if it can do it, because in this case, corresponding to each value of x, there is only one value of y. So this should in principle be fitted by our neural network. So let's see if we can fit it. The rest of it is the same. We don't need to rerun this particular thing, because it's just the definition of the neural network. So I'm initializing the neural network with 10 neurons in each hidden layer. Okay, and now I'm just going to plot the initial random guess of the neural network. And you see that the actual data looks like this. Sorry about the aspect ratio. Okay, this is not an ellipse; it's just a circle, but the axis is skewed. That's why it looks like that. So the initial neural network is of course completely random. It is showing that the function is this red line, which is completely wrong because it has not learned anything. But now let's try to run the optimization algorithm. Okay, so now let me rerun this. Again, in a notebook environment, you just have to press Shift Enter again. But please be careful about the order of execution. Okay? One of the problems that you have in running a code on the notebook is that the order of execution is not the order that you see. Okay, and you can look at that very easily here. For instance, this shows that this is 73, right? Which means that this is 64, this is 73. Right, so this instruction was not executed after this. In fact, if you look at the previous one, this is 72. The 72nd instruction that you executed comes before the 64th instruction. Okay, so this can cause all kinds of random problems with your code. It might look as if you're reading linearly, but your program is executing differently. So always be careful to maintain the order. That comes with a little bit of practice. But if you're stuck, there is always a restart and run all command, which will erase all history and rerun it sequentially. So in case if you're running into problems and using notebooks, and if you get random results, this could be one of the problems. So be aware of that. Okay, so I've done this. So now let me train the neural network. So this better work, okay, because it's supposed to learn. So let's see if it works. Now, okay, it's running. You see the loss is decreasing. It has come down to 0.05, right? So initially it was, the loss was 0.79, and now it has come to 0.05. So let's see what it looks like. What does the learned function look like? Okay, it's still not good, but it is moving somewhere. Okay? It's moving somewhere, but it is still not good enough. And probably this is not enough number of iterations, or the learning rate is a problem. So maybe you will have to change the learning rate, increase the number of epochs, and maybe I don't want to print everything. So if I just run this again, maybe with a larger number of iterations. So you see that the loss has now come down to a larger value. So maybe this would be a better fit. We don't know. So it's getting better. So you see that initially it was the initial prediction, which was plot x is initial. Okay, so I'll just plot it here just for reference. So this, okay, yeah. So I've just plotted out the initial value of the neural network, right? So initially it was randomly initialized, and so obviously it was giving some nonsense curve like this. But after training, you see that it's slowly getting there. But it's still not entirely, it has not gotten the full curve yet. That's because it is not trained completely. Okay? So it takes a lot of iterations to learn in this particular case, okay? Because we're using a very big neural network for a very simple function. Maybe reducing the size of the neural network should help. Okay, so I will leave it to you to play around with this. Okay, which is, for instance, you can change the architecture of the neural network, which is as simple as changing this, right? So if you want to change the number of layers, the number of neurons per layer, etc., you can change the optimization algorithm. You can use stochastic gradient descent or Adam or any of the other fancy algorithms. You can play with the learning rate, etc. And depending on that, you will get different results. Okay. So the point of this exercise is to just show you that you can use deep learning. It's a very fancy word, but if you are not aware of what is happening, you can get all kinds of nonsensical results. Okay, and in this particular case, you see that you have used a very fancy deep neural network. Has three hidden layers and whatnot, and I mean it's not really deep in modern sense, but at least you have some neural network. The loss is decreasing as you would expect from a gradient descent algorithm, even though it's a stochastic gradient descent. And you see that it is still not learning the full function. It has just learned an approximation. It's getting better, but you need to probably run more. Okay? So So these are all things that you should keep in mind. Okay, the solution that you get from a deep learning algorithm may not always be the right one. Was there a question? Oh, sorry. I thought I heard some sound. X1 seems. What is that? Oh, it was a long pack. Okay, something else. Was there a question? Okay. Okay. So what I'll do now is to, rather than running this code again and again, instead of cutting and pasting, I'll show you the results of code that I have already written for you, and which you can also find in this particular web page. I've given you the link, right? So you can look at that. I'll just go through the code so that you get the larger picture of what is happening. Okay? Now, if you look at this particular case, right? So we have seen that if you, sorry, scroll up. Yeah, if you were to just run a supervised learning algorithm for this data, you will get a nonsensical result. Right? And the reason you get a nonsensical result is because it is a nonsensical endeavor to fit a function for this data. This data is inherently not describable by a function. It's an implicitly defined. It's the original function is implicitly defined, right? So it's a one-dimensional manifold in 2D space, which cannot be represented as a graph of a single function mathematically. That's the reason why this fails. So is there a different way of doing this learning that will help you get out of this particular problem? Now, what we know about this, right? I mean, is that this data is generated by a circle, which is of this particular form, right? X squared plus y squared equals 1. So what we know about this system is that it satisfies this equation x squared plus y squared equals 1. In more complex situations, this would be encoded in the form of a differential equation or something you know about the physics of the problem. Okay, what if you use that information instead to learn this particular neural network? Let's see what happens with the same circle neural network. So data points on the circle. If you use the standard neural network, you would get a nonsensical result for good reasons. Let's see how you would do it if you encode known information about this function. And that is what is typically called as differentiable physics. So in this case, what we will see is that we will not even use the y values. We'll just use the x values alone, because we know that y depends on every x according to an equation. Okay? We're going to use that equation as a loss function. So you initialize the data, you prepare the data just as in the previous case, you set up a neural network just as in the previous case, but here comes the interesting part. The loss function is different. Okay? Whereas initially, if you look at your example, right, so the loss function looks at the discrepancy of your data point and the predicted value of the function. Now you're going to look at the predicted value. There is no actual data involved, but you're going to use the known information about the physics. You know that if the data point is correct, then the sum of x squared plus y squared should be equal to 1. So any deviation from this can be used as a loss. So you use this particular, the squared value of this, which is always a positive quantity, as a loss. Okay, and when you do that, you can, the rest of your training algorithm is the same. Okay, so you create an optimizer, you compute the loss function, and then you have your favorite magic keyword backward, magic function backward, which computes all the gradients for you. Then you compute the loss, and this is just the standard gradient descent iteration step. And when you do this, okay, when you run this code, please feel free to run it. Okay, the reason I provided the Python files is that you can actually download the code, run it, and see this for yourself. Okay? And every time you should get a different result. You see that the loss is actually coming down to 10 to the minus 2, in contrast with the fact that it was staying at 0.5 earlier. And when you plot what happens, something very peculiar is happening. It learns one of the branches at random. Okay, so even though we're using the same data, the physics-based algorithm is able to get one half of the branch, okay, one branch of this particular data set properly. This is the best you can do with a given function. If at all you want to represent it by a function, the best you can do is to learn a part of the manifold that can be expressed as a graph of a function. This 1D manifold. Okay, so in this case, it learns the lower part of the data set using this particular function. But if you run it, you might actually get the upper part. It depends, because it's a stochastic algorithm. Every time we run it, the results will be different. So what I see here will be very different from what you see, but it would learn one of the two branches. But even this simple example, right, it tells you something very profound. If you look at this data set, okay, so you see that it already looks very different and in different iteration. So in this particular case, the yellow dots, which almost look like a straight line here, that represents the data set. The red points represent the solution that is learned by a deep neural network. So obviously it has completely missed the entire data because it's trying to optimize for both the top branch and the bottom branch simultaneously, and it misses both and computes the average instead. So it computes something that lies between the upper and lower branches, which is completely wrong. So if you were to make a prediction based on inference based on this neural network, you would be completely, making a completely wrong prediction, right? So this is something you need to keep in mind, okay? When you're especially dealing with non-convex optimization, which is what we are doing here, you can learn some really bizarre solutions which are completely wrong, which are completely non-representative of what is happening. And this is especially important to keep in mind given the fact that everyone is interested in using a deep neural network now. It's not a silver bullet. You need to be careful about how you use it. But if you use a physics-based learning where you encode information about the known function, then you see that with appropriate training, it actually learns part of the data properly. It's not capturing the full data. This is the best you can do given this data. Of course, if you use a physics-based learning for just one, with the data set being just on one half, it would capture it properly. That's not an issue. Okay, so this simple example shows you how for the same data, a supervised learning algorithm is different from a physics-based learning algorithm. Okay. Now, I think this is a good time to also pause a little bit and see if there are questions, if you want to discuss anything, and also I want to ask Akshay, how much time do I have? But we started at 2:30, right?
Yes, yes. So technically we are like at so 3 hours, 2 sessions, which means that we can go up to 5:30 according to the schedule.
Okay, but why don't we take a small break so that in case people want to just assimilate this, they can have some time, or they want to take a
Sure.
small break. So we'll meet again at 5:15. It's just a
Okay, so I'll
4 minute
take this
break.
opportunity to make an announcement.
Yeah, yeah,
So
sure.
tomorrow is the session for that health and well-being, and it's the session will be held on Zoom. So I have already emailed you guys the details. It would be nice if you could. So sometimes that Zoom needs to be installed. So you can just check if you have that Zoom. Other than that, all the password and link have been sent in the email. So make sure that you have that email. If you don't, let me know. I'll send that email again. Also note that the meeting will start at 10, not 9:30.
Sir,
So,
we received that mail, sir.
huh?
We received that mail, sir.
You have received the mail. That's good.
Yes, sir.
That's good. Just make sure that you have that Zoom thing working, and that will start at 10. After 10, there will be a 15-minute session for feedback. I'll create a Google form. You will get 15 minutes or maybe 10 minutes depending on how many questions there are, and you will get one chance of attempt, right? So you fill it, you submit, and then you are done. So that is the assessment. You should get 80%, right? Or there is some criteria on AICTE website for the certificate. So make sure that you have that. If you have attended all the classes, I think it will be straightforward. If you have not attended the classes, well, let's see. Okay, that was for the announcement for tomorrow.
Yeah, we still have a few minutes. I think we can give a small break. Regroup at 5:15.
Sure.
In the meantime, if someone wants to chat, you're welcome to chat. Or if you want to enjoy a moment of silence, that's also fine with me. Academy is full of
That statement is a little bit dangerous. 2 minutes of silence.
yeah. Well, no, I'm happy with silence. My throat is parched, and I would like to really appreciate not talking. But if you want to talk, I'm happy to hear.
No, I just wanted, because I'll forget. I know I'll forget at the end. So I just wanted to make that announcement.
Yeah.
Okay.
So it looks like I might not have enough time to get into the details of all the rest of the talk. So I'll probably give an accelerated uh, overview and wrap it up by 5:30 or 5:35. I don't want to exceed the time limit because I think many of these also involves actual coding, and given that people don't have a background in Python, and I think it might be a little too much to do the live coding. So
I think one of the candidates was asking me about it yesterday, that how bad is it? It's like I have not done Python. I'm like, no, don't worry. It's not the regular coding. It's fine. It's just some packages. You import some packages, use those functions. So it's like,
yeah. No, but even on top of that, there is a significant amount of coding, but I think it's not really difficult coding. Yes, absolutely, I agree.
I mean, we conventional coders would. I mean, I don't know. There is, I guess, a lot of inertia with us Fortran coders.
Uh-huh.
So we don't want to move from our forte.
Right. No, Fortran is nice, but I think that there are certain things which are easier, much easier with languages like Python or Julia.
See, part of
Yeah.
that comes from. So people also misuse that.
Yeah, true.
So, for
Yeah,
example,
absolutely. Yeah.
so I teach a computational course, programming course,
Uh-huh.
and I have to teach them how to program, right? Code, how to write
Yes,
functions.
yes. Mm-hmm.
And people often come up with, can I use MATLAB? Can I use
Right.
R? And I'm like, no. You are supposed to learn how to code.
Yeah, that's true. That's absolutely true. Yeah. No, that kind of coding discipline is important. Yes, I mean, so one of my favorite languages is C, not C++, but C,
Yeah.
because I think it really takes you to the metal and really helps you understand how things work. And Lisp, of course, Lisp is even more beautiful, but
Lisp is older, right?
much older. But it's, I think, the language in my opinion, because it's the
I
level of expressivity it has is just amazing.
see. I learned COBOL. I learned there was one more, COBOL and Pascal.
Uh-huh.
In school days, they used to teach us GW Basic, COBOL, Pascal,
Uh-huh.
Fortran, the old version where you have that 80 column and 7 column and strict sense of formatting.
Yeah,
So
really takes it to the 50s and 60s. Yeah.
nowadays, I mean, I find it sometimes difficult to catch up with all these new languages. So I mean,
Yeah. Yeah, that's okay. Anyway, we are hitting 5:16. Should I continue?
sure, please.
Okay. Yeah. Okay. So with that, I mean, so what we have seen so far is, just to go back to the initial uh, overview, right? So we have looked at these parts. Okay, we have seen all these, which is we have looked at what differentiable physics is in a very broad sense. We reviewed basic ideas in optimization. We looked at automatic differentiation and tried to implement that using some code. And we also saw how to what deep neural networks are and how you could implement them using Pytorch not in every single detail, but at least you have some basic idea of how it's done. Now, what I want to do in the remaining time is to very quickly go through the applications. One application, which is ordinary differential equations. So my research area is in partial differential equations, among other things. I work in solid mechanics to understand behavior of solids. I mean, they are typically modeled with partial differential equations. That's true with fluid dynamics also, and partial differential equations arise in a very lot of different applications. Okay, but they are more difficult to understand than ordinary differential equations, which are much simpler in that substance. Right? So what I thought was to use a simple example using cricket ball trajectories, but it looks like 3 hours is too short for getting all the details. So unfortunately, I won't be able to get to this competition. I really wanted to get to this competition and ask all of you to virtually do bowling and train neural networks to do bowling and see who does it best. But it looks like we won't have the time to do it. But that's no reason to stop yourself from not doing it. Okay? The code is out there. Feel free to play with it, experiment with it, and it should be fun. So what I'll do in the remaining time, in about 10 to 15 minutes, I will very quickly go through the application of these deep neural networks or these kind of optimization algorithms to ordinary differential equations, and discuss both the forward problem and an inverse problem. Okay, the forward problem simply means how do you solve an ordinary differential equation. An inverse problem is more involved, where you want to see what should be, how should I set up the ordinary differential equation so that I meet a particular objective. Okay, and we will see very quickly how these are done, and I'll show you the code. I won't explain everything, but give you the larger picture. Okay, and I trust that if you are interested, you can always learn the basics of Python and also use the code as a starting point to dig deeper. Okay, good. Okay, with that, let's move on. What we want to do is to see how you would solve a differential equation using deep neural networks. Okay. Now, suppose you have a simple ordinary differential equation which tells you that the derivative of a function x, which depends on t with respect to t, is some specified function f. Okay, and you're given some initial condition at time t equals 0, x takes the value x naught. Now, your goal is to compute the solution over an interval 0 t. Okay. Now, if you have an analytical solution, that's great, but that's rarely the case. Okay, typically we do not have an analytical solution, and often you will have to resort to numerical approximations. There is a entire beautiful theory of how you would do numerical approximations. It's a very classic branch of numerical analysis, but I won't have time to talk about that now. Rather, I want to talk about a recent trend, okay, which is called as physics-informed neural networks, which try to approximate the unknown solution by a deep neural network. After all, a neural network is just a function, a parameterized function. So you represent the unknown solution here, which is x, by means of a parameterized neural network, x hat of d theta. Once you do this, then you need to recast this differential equation as an optimization problem so that you can solve the differential equation using the same ideas that we discussed, gradient descent and all the ideas. So how do you convert this particular problem, ordinary differential equation, into a optimization problem? And recall that when we studied physics-based learning, what we said was that if we know something about the physics of the problem, then we can use that to decide the loss function. In this case, what we know is that the discrepancy between the first order time derivative of x and the function f evaluated at x of t should be minimal. Okay, so the dx by dt should be as close to f of x comma t as possible, preferably 0. So a way to encode that is by using this quantity. So what you're seeing here is just the difference between the left-hand side and the right-hand side, whole squared. Now, in the ideal case, the smallest value of this is 0, which would exactly mean that this differential equation is satisfied. If the discrepancy is large, then your candidate neural network is a very bad solution candidate. So of course, t is a continuous variable. So what you do is you instead do a discrete sum. So ideally, you would like an integral where you take the difference of these left-hand side and the right-hand side, square it, and integrate over the whole domain. But we cannot handle integrals, continuous integrals on a computing algorithm. So we discretize the integral. It's called numerical quadrature. And the simplest kind of a quadrature is where you have equal grid points or whatever. So this is a simple, you pick a set of sampling points which are specific time intervals in the interval 0 to capital T, and you form this loss function. Okay, and you see that this is actually a loss function that depends on the parameters, unknown parameters of the neural network. But this is not the entire loss function. You also require that the initial condition is satisfied. Okay? Without the initial condition, the ODE solution cannot be found. There are infinitely many solutions which satisfy this equation. Providing the initial condition fixes which of the infinite family is your actual solution. Okay. So the way you enforce this constraint is, again, go back to our simple idea. We use a penalty approach. Right? So you penalize deviations from the initial conditions, and you have an appropriate constant to enforce that penalty, and that's it. So what you have is a loss function. Okay, your neural network is a function that is parameterized by theta. Okay, that's the first part. So if you look at your optimization algorithm, you need a function class, you need a loss function, and that sets the minimization problem. So the function class is given by this neural network, right? X hat of t comma theta. The loss function is given by this particular loss, which is a sum of the interior residue, okay, this particular quantity, the difference of the left hand side and the right hand side, that's called as a residue of the differential equation, the squared residue plus a penalized version of the initialized condition that sets the loss function. So you have the loss function, you have the function space, and you have the minimization problem, which is minimize this loss with respect to that particular function space, and that's it. Okay. Now, this simple idea is quite old actually. It was proposed in 1998. I presume there were other references earlier too. I'm not sure. But you see, this is a very old idea, but no one cared about it at the time because Google and Facebook were not there to push it hard enough. But now that Google and Facebook are pushing neural networks, and everyone is like, "Oh, what excited about neural networks?" People have essentially, reinvented the same thing, and it's called in its new avatar as physics-informed neural networks. Okay, so it's a very fancy term for a very simple idea, and all it does is basically this. You encode the known information about the differential equation into a loss function, and then you minimize that loss function with respect to a specified neural network class, and that's it. Okay, so the rest of the details are very similar to what we did earlier. Earlier, we just had a simple data set, so it was very easy to fit the data with a function. Okay, at least one branch of the data of the function. But now we have an entire differential equation, right? So how do you go about doing it? Okay. Now, what I'll show you now is to go through, very quickly go through the code that tells you how this can be done. And for comparison, I'll also implement a very, very simple traditional numerical method, which is a forward Euler method. What it does is basically it replaces this derivative with a finite difference approximation. So you use a standard finite difference approximation for the left-hand side, and you use that to march the solution in time from a given initial condition. Okay, this is something that is done routinely. And I should also mention while I'm at it that the forward Euler is probably the worst choice for a numerical integration scheme. Okay, there are far better algorithms, but our goal here is to illustrate how things work. Okay, so the simplest algorithm is good enough. So if you go back to the notebook that I had shared, right? There's a third section, I think, yeah, which is solving differential equations. And I've taken this simple differential equation for concreteness. So you see that the derivative of x is this function 2 pi cos 2 pi t. In this case, we have an exact solution, which is given by this. Typically, you don't have that. So what I'm doing here first is the simple forward Euler discretization. This is a simple finite difference scheme. You see that the derivative is discretized. Dx by dt is written as xn plus 1 minus xn divided by delta t. So you rearrange that, you get this very simple equation. And the implementation of that in Python is very, very straightforward. Okay, so all you have to do is to define this right-hand side, which is 2 pi cos 2 pi t. And then the forward Euler algorithm essentially amounts to saying that x is xn plus 2 pi, whatever, that's exactly the same thing. Right, so it's a very simple idea, which is then looped over as many iterations as you want. And then in this case, you know the exact solution, so you can compare it. Okay, it's not great, but it's a reasonably good fit. Okay, and as I said, the forward Euler algorithm is not the best algorithm to use, but we want something approximate to compare the results of our neural network. So this is just for comparison. So how do you define solve this with a neural network? The procedure is entirely the same. Okay, you first initialize the data set, and then you create a neural network. In this case, I'm creating a neural network which has one input, which is time, and one output, which is x of t, x hat of t. And in this case, it has this architecture: 1 times n times n times 1. So it's a 2 hidden layers network with n hidden neurons in each hidden layer. And then I'm using a tan h activation function. So this is exactly the function that the neural network computes. Now, the key thing in physics-based learning is that you're using a different loss. You're not using a loss, the egg-headed loss like an L2 loss that people use in machine learning, without understanding what the physics of the problem is. We know better, right? We know that the differential, in this case, the neural network represents a function which satisfies this differential equation. So we want to encode this differential equation in the loss, and that's what we saw in the slides also. And that is exactly what is implemented. Let me show you here. Okay, so if you look at this particular function, what it does is it implements the law. So you see that here it computes first the derivatives using simple finite difference, and then encodes the loss directly using the ODE itself. So this is the ODE. I'm using that ODE as a way to encode the loss. Okay, this is the whole thing. If you look at these three lines, this represents the first term. If you look at our slides, the first term that you see here, that is the interior loss, is represented by these lines of code. The boundary loss is basically a weighted, penalization of of how much the initial condition varies from the specified initial condition, and that's what is given here. So the total loss is just a sum of the weighted sum of the interior loss and the boundary loss. That's it. The rest of it is the same. You set up, you train the neural network, and you have this magic keyword, magic function backward, which is a favorite function now. If people say you have to go forward, but in machine learning you need to go backward, which is, I think, true in many ways. When people apply machine learning in science, I think they actually unlearn a lot of things. So it's important to not lose out on the physics. So when you run the backward function on loss, you basically compute the derivatives, and then you use your favorite optimizer to step through it, and that's it. The rest is the same. So let's see how it performs. And once you run the algorithm, you see that the loss actually decreases in this particular fashion. I've plotted it on log scale so that you can understand clearly how drastic the drop in the loss is. And then you can see how the function evaluates. So here you see very clearly that the exact solution is not clearly seen. It's a black line. The blue circles represent the approximation which is computed by the finite difference algorithm. And the red curve tells you what is learned by the neural network. So you see that the neural network has indeed learned the solution to the differential equation using the physics-based loss. Okay? But there are a lot of caveats here. Okay, if you use this algorithm blindly, if you extrapolate what happens after this, the neural network will give completely random answers. Okay, so even though there is a lot of hype about this method, physics-informed neural networks, it is very slow and it is no match for a traditional numerical solver. Okay? So please keep that in mind, and that is true also in many other applications of machine learning and science. So there are certain applications where I think you can have a lot of insight coming from the use of machine learning, but in many other applications, it would actually it's actually a bad idea to do that. Okay, so it's important to apply some kind of discretion in choosing when to apply machine learning tools and when not to apply it. So good. Now, finally, I want to show you an example of an inverse problem. Okay, I wanted to really spend more time on this, but given the constraints, we have to look at this very quickly. Consider the same differential equation, but now I ask you a different question. I don't tell you what the initial condition is. I'm going to ask you, what should the initial condition be if finally this condition has to be satisfied? So let's say that you choose some initial condition, you integrate this differential equation in time, find what is the state after a time at a time capital T, and you evaluate some function j. Okay? And then if you require that j equals j naught, what should that initial condition be? Now, this is a very abstract way of stating this. Let me give you an example. Suppose that you're bowling. Suppose you're a fast bowler, and your initial the trajectory that your cricket ball follows is given by some differential equation. In fact, I'll show you some equations later on. Now, the initial conditions could be the speed at which you bowl the ball, the angle at which you release the ball, etc. So those are initial conditions. Now, what could be an objective? Finally, you want the ball to hit the stumps. So it should be in a certain region in three-dimensional space. So it should be in that region occupied by the stumps. So you want that condition to be satisfied. So what should the initial conditions be so that you can reach that objective? Okay, in a forward problem, you're given the initial conditions. You're saying that, okay, these are the initial conditions. The bowler is bowling at this speed, the angle of release is this. What is the trajectory? That's easy. But the inverse problem is, if the ball has to hit the stumps, what should the initial conditions be? Okay, so that's a more involved problem. And so in other words, you want to find something about the initial conditions. This is an example of an inverse problem. This is not the only kind of inverse problem. There are many kinds of inverse problems, but this is just to give you an idea of how things work. Okay. Now, the strategy that we will follow is what is called as a shooting function method. I think Professor Hota talked about it yesterday. There is a lot of similarity between this and optimal control. So you should not be surprised to see some connections. But the idea is very simple, right? What you want to understand is if I tell you the value of J naught, you want to find out what that corresponding initial condition X naught should be. So learn this map that goes from the output, desired output J naught to the input X naught as a neural network. The information about the differential equation flows forward in time, but the neural network learns something in the opposite direction. It learns from the output J naught to the input X naught. If I tell you what the J naught is, what should the X naught be? So it's the equivalent of saying, suppose that I give you a cricket ball and then I randomly place a stump at some point in the cricket ground and tell you, bowl such that it hits the stumps here. So I tell you what J naught, which is the position of the stump, is, and you need to choose the initial conditions, your speed and angle of release, etc., so that it hits the stump. Right? Now, what I'm telling you is you're going to learn that association, the position of the stump to the initial conditions of the ball's delivery of the ball, as a neural network. That inverse function, that function is what you will learn as a neural network. And this is an example of an inverse problem. It's not the only example. And again, the loss function is our discrepancy. We want, if you choose your to approximate this particular differential equation using a neural network, you get a final solution. You want the discrepancy between the value that you want and the value that you specify to be as small as possible. So you use that as a loss, right? Now the key difference is if you put it into the loss function and then you differentiate it, you see that it has three distinct terms. The first term is just the difference between the expected value of the objective, the function that you want, and the specified value. This is easy to calculate. The last term is just the gradient of the initial condition with respect to the parameters, which is exactly what the loss dot backward is. Right? So if you look at this part, the final term, the gradient of x is not with respect to theta, is basically the loss of the neural network, which we know how to compute. At least we have seen a few examples of that. But the central term tells you how to compute the loss, how to compute the gradient of a finite difference solver. Now, this is a classical solver. Now you're going to approximate the solution of this particular equation, not with a neural network, but with an actual physical solver, like your finite difference algorithm. So if I start with an initial condition x naught, and I use a step size, let's say h, and then I integrate it forward to n time steps, I get xt. Okay, so I have this map which takes x naught to xt. That's called as the discrete flow map. Right, so it takes the initial condition, it tells you what the final position of the ball is. It takes x naught and gives you what xt is. That can be computed by any of your regular solvers, your finite difference algorithm, or any other standard classical numerical analysis. Now, if you look at this loss function, it contains this term, which is the gradient of that standard physical solver. Now, we know how to differentiate a neural network, or if we know how to differentiate functions using automatic differentiation, but how do you differentiate an actual solver? Right? If I give you a finite element program, how do you differentiate a finite element program? If I give you a lattice Boltzmann code, how do you differentiate a lattice Boltzmann code? Okay? The answer is not obvious, but all you need to understand is that if you break down the way it transforms the input to the output, and as long as you can express that algorithm, entire algorithm, as a computational graph, if you can understand the computational graph of that algorithm, you can differentiate the heck out of it. Okay, not all algorithms can be differentiated. Okay, for instance, many of the heuristic algorithms like simulated annealing, Monte Carlo methods, genetic algorithms, these are all algorithms which cannot be differentiated because they do not have the structure. They are based on random moves. But if you have any of the other traditional solvers like finite difference, finite volume, or the numerical methods for molecular dynamics, etc., these are all things that can be differentiated. Okay, as long as you're able to express it in this, if you understand the elementary operations that act on it. So what I'm going to show you is an example of how to actually differentiate a finite difference time matching scheme. So we saw that we solved this differential equation also by time marching, right? So we looked at a forward Euler discretization. I'm going to tell you how to differentiate this particular algorithm itself, like forward time marching itself. Okay. Now it turns out that doing this is not difficult at all in Pytorch, as long as you implement each of the individual steps in Pytorch. It's going to be slower than implementing it in standard Python, or much slower than implementing it in Fortran or something. But here's an advantage of why working with Python is more advantageous than working with older languages like Fortran, because you can differentiate through a program. What does differentiation mean? If I have a standard solver, I take an initial condition. I know what the final output is. What if I change the initial condition slightly? How does the output change? In a standard solver, you have to reset the initial condition and run the entire solver to find what the change is. But if you can differentiate the solver, then all you have to do is, if I tell you the starting point, I also add a gradient information at the starting point. That automatically tells me how the values change. Okay, so it saves up on a lot of computational time, especially if your solver is very costly. So in that cases, you want to differentiate the solver. So how do you do that? And I want to give you an example with cricket. I actually wanted to give a competition based on this, but it's not happening. So the idea is very simple. Suppose a bowler let's take a two-dimensional section, and let's say a bowler releases the ball at an angle theta. There's a total height of the bowler, and then you have the stumps. Your goal is to hit the stumps. Okay. Now, what you want to know is, suppose I tell you the wind speed and the bounce of the pitch. I want you to find out what should be the initial speed of release and the angle of release, bowling and angle of release, so that the ball hits the stump. Okay, that's a very simple thing. Now you see that this is an inverse problem, right? So I give you conditions, and I want you to find the ground conditions, and I want you to find the bowling initial conditions. You use that map as a neural network, but your entire cricket ball trajectory is computed using the known physics of the problem. In this case, we know how the cricket ball trajectory can be approximated. Okay, there's a very nice paper which was published in 2009. I mean, there have been lots of people working on this game physics, but I like this paper especially because it does a good job. It also tells you how to compute the swing of the cricket ball. Okay, my original example was in 3D. I wanted to have a competition about who is the best swing bowlers. Okay, that gave rise to this particular result. You see that the ball is actually swinging and hitting the stumps. I wanted to simulate that, but then I thought 3D was difficult, and then I reduced it to the 2D problem. But it looks like we don't even have time for the 2D problem. So it is what it is. The goal is you know the physics of the problem, right? So if, in this simplified 2D representation, if I look at the cricket ball, this is the trajectory. You know the drag force acting on this, which is captured. All the complex physics about the fluid dynamics is captured in this CD. By the way, fluid dynamics people are the original machine learning people. Okay, they looked at a very complex problem like turbulence, and they said, screw that, I'm going to replace that with a single quantity, which is CD or any of these non-dimensional numbers. So they learn all the complicated physics with these very simple non-dimensional parameters. Okay, that's right there an example of what machine learning people aspire to get. Anyway, so you see that this particular equation, these two equations, which tell you how the velocity of the ball changes as a function of time. U and V are the horizontal and vertical velocities. W is the wind speed, G is the acceleration due to gravity, and CD is the drag coefficient, which tells you how, if you have a wind or whatever, if the cricket ball is flying through air, so it'll experience drag. So the interaction between all these forces is what dictates the motion of the cricket ball, and it's governed by these equations. So what you really want to do is, if I have a neural network that takes the final position of the ball and gives me the initial conditions, if I want to implement a optimization problem, not only should I differentiate the neural network, but I should also differentiate this entire trajectory, which I could say implement with an Euler method. Can you do that? Okay, the answer is surprisingly yes. Okay, and I'll show you very quickly how that looks like. So this is just setting up the forward problem to show you how the cricket ball trajectories can be simulated. There's no differentiation involved here. It's very simple. So you see that here is one ball which misses the stump, here is one which hits the stump, etc. Right? Now, for the inverse problem, you first set up the neural network, and then you proceed as follows. But here is where all the magic is. Okay. Now the loss function, in addition to computing the loss of the neural network, also computes the discrepancy between the final position of the ball and the position where you want it to be. And that is actually computed by a finite difference algorithm. The beauty of this particular way of doing this thing is that you're combining a traditional scientific solver with a modern deep neural network, and if you implement it using a language which is differentiable or a framework which is differentiable like Pytorch, you can differentiate the entire thing. You can differentiate the entire chain. Okay, and that is what is done here. And indeed, the rest of it is the same. You set up the training process, you train your neural network for the inverse shooting function, and then you can see that it actually learns how to hit the stumps. Okay, and you can test it on a variety of different conditions, and it's actually able to uh, perform well. Okay, now the original competition I had in mind was I was thinking about letting each one of you develop your own neural networks and give you all 5 overs to bowl, and whoever gets the maximum accuracy is the winner. But uh, I suppose you can do the competition yourself in your own free time once you understand the details. Sorry that I could not go through the details, step-by-step details of this. We're running out of time, but hopefully this should tell you that there is something exciting. And even though this example is in the context of cricket ball trajectories, this idea is very, very powerful. And oh, sorry, was it a question?
No, no, no. I just.
Yeah, last slide. I'm done. So this idea is very powerful. Okay, you can also apply it to solve partial differential equations, very complex solvers. It could be like the kind of lattice-Boltzmann course that Professor Akshay studies, or it could be a Navier-Stokes equation, or it could be like solid mechanics where you study equations of elasticity or plasticity. As long as you're able to break down the solver into differentiable bits, you can combine them with modern deep neural networks and then create some interesting new knowledge. Okay, that's the whole drama. A lot of my current research is exploring this particular connection. And while I'm on it, I didn't talk about this, but one very serious problem with neural networks is that they are black boxes. The sense that even if you learn this function in a particular function space, you cannot interpret what it does. And this is a serious problem because, especially in science, interpretability has a lot of premium. Okay? So, how do you develop interpretable neural networks? So this has been something that I've been very interested in, and recently we published this work in JCP, which takes a first step towards that. So, please feel free to check out our work. We call it SPIN, and this is work jointly done with Prabhu Ramachandran. I mentioned how he created Mayavi and Fossil. So he's a very close collaborator of mine, wonderful collaborator. We recently published this paper, and you're welcome to check out this for more. Check this out for more details. And if you are interested in the larger subject of physics-based learning, there's recently an online textbook, physics-based deep learning, which came out, and it also has a source code available, so you can also experiment with various kinds of these combinations of traditional solvers and deep learning solvers, deep learning algorithms. So it's a very active and exciting area, and I'm hoping that this presentation would help you. If you're interested, it would propel you to look further into this. Okay. And so that's pretty much all I have. I'm sorry that I exceeded the time by 20 minutes. And I'm also sorry that I could not get into the details of the applications to differential equations to as much extent as I would have desired ideally. But, we have a finite amount of time, and that's just the best I could do. So I hope you enjoyed it. Thank you very much for your time, and wish you a very happy winter break and also a very happy new year. Okay? I'm happy to take any questions that you might have. I'll be around. So
Sir, I have one question.
yes,
Sir, if you can give more light to that, it is not interpretable.
yeah. Oh, you want me to talk about? Okay, yeah.
Yeah, yeah.
Yeah. So what happens is that if you let's take a very simple example. Okay, suppose that I want to learn a function. Let me write it like this. Suppose that my function space, right? So you want to minimize over a function space f, right? So suppose my function space is the set of all linear functions. Okay. Let me first write it. Oh, right. So suppose that I have I'm looking for the best function. Let's say in my optimization problem. Yeah. So this is the problem we are dealing with, right? So you want to minimize some loss function, objective function, with respect to a function's class. If I choose my function space f to be this simple space consisting of linear functions, right? Now, this is entirely interpretable because if I learn some values of a and b, which simply means that I run the optimization algorithm, find the best values of a and b, then I can query the function. I can understand that there is a linear relationship between the input and the output, and b tells me how something about this dependence. If b is very small, it tells you the dependence is weak. If b is very large, the dependence is very strong, etc. Right? So this tells you something about it, and you can interpret what is happening. Whereas if you take a neural network, a standard deep neural network, right, it's going to be a function like this. So sure, if I give you an input, you can always compute an output. In fact, we did that. Right? But what does it tell you? Once you finish learning the neural network, which means solving the optimization problem, you get some values for this parameters theta, which is the set of weights and biases. But what do these weights and biases mean in the context of the particular application? So let's say that you're trying to solve a differential equation with these neural networks. Okay, fine. I get a neural network that fits, you know, going back and forth. I'll take the PDF. It's much easier to browse. Yeah. So let's look at this example, right? So your neural network in this case takes one input and gives you one output, and it is able to actually get the curve. But if you look at the parameters that is learned by the neural network, it's some complicated set of weights and biases. What do those weights and biases have to do with this particular function? That's not an easy question to answer. There is no way to interpret what the nodes and weights are. This is in very sharp contrast to what happens in traditional numerical analysis. Let's say I have a finite element model to understand a particular application, let's say. If I solve the problem, I can query the unknowns, which are the nodal values, and they have a very, very precise physical meaning. Okay, they tell us what the value of the unknown is at that particular mesh point, etc. So you understand what it means. Whereas in a neural network, if I ask you what does this weight mean, there is no better answer. There is no good answer for that. The only thing, the best you can say is that this particular combination looks like this. That's it. You cannot tell what that particular weight means, unlike traditional solvers. Okay? This is very problematic in science because you can have very, very different set of combinations which look curved like this. And what does it even mean, right? So there is no way to interpret the solution. And that's a very serious problem with neural networks. So can you get around that problem is the question that I was talking about.
Yes, sir, yes, sir. So parameter selection is dependent on the problems that we are solving.
Not just that, even if you select the parameters, what those parameters mean is not clear.
Yes, sir, yes. Oh,
Yeah. So
thank you, sir.
what we have been developing are a class of neural networks which are fully interpretable. Okay. So in particular, what we have shown is that if you generalize the classical radial basis function networks, you can create a class of neural networks which are more complex than RBF networks, but which are less complex than a fully dense network, but which can be fully interpreted. So you can look at our paper for more details. Just here. So I've given the link
Is
here.
that
Again,
paper available online?
yes, you should be able to. The archive link is available. So if you just search for this, you should find a free version on archive. Okay? So if you search for this on Google, then you will find the archive link. The archive link is completely free to download. If you have a subscription to JCP, you can also download it directly from the JCP website. So not just the paper, all our code is also completely online. Every single result that is produced in this code in this paper is reproducible. So we have a GitHub repository for all the code. So you can actually look at the codes that were used to generate the results, and you can reproduce them yourself. I think that is a very important thing in research, which is often missed. The science is supposed to be reproducible, right? So I mean, a lot of times what happens is that in the rush to produce a lot of papers, people often have their own in-house codes, which is not a bad thing necessarily. But then I think it's nicer to have a transparent system. And so what we have been trying to do is to make everything open source, so that it's all built on open source tools, and the code is also available. The individual runs are also available, so you can play around with it and